Prepare for a job interview about deep learning with this course from Tatev. She goes over 50 common interview questions related to deep learning. She's an experienced data science professional and has published papers in machine learning scientific journals.
I'm Tatev from LearnerTech. In this course, I'm going to teach you everything that you need to know from the topic of deep learning. I'm going to help you prepare for your deep learning interviews. We are going to answer 50 most popular deep learning questions out there that you can definitely expect if you are going to participate in data science, machine learning engineering, but also AI engineering and research scientist interviews. Deep learning is one of the most popular topics these days because it forms the cornerstone of topics such as large language models, but also the generative AI. It contains many complex concepts. It combines linear algebra, mathematics, differentiation theory, and also advanced algorithms, and they all come together to form this field of AI, which is the fundamental part of generative AI, the large language models. So if you want to get a job in large language models or Gen AI, then definitely prepare for this type of interviews because deep learning is going to be a concept that your interviews will test you for. This course I have specifically designed in such a way that we will go from very basic questions to a more advanced one. So let's first look into the first 50 questions that we will be covering as part of this course. The first 10 will be the basic concepts. So we will start very basic. We will talk about the concept of deep learning, what is the difference between deep learning and machine learning. We will also talk about the concept of neural network. We will look into its architecture. Also, what is the concept behind neurons? What is backpropagation? How does it work? How it is different from GD? What is GD? What are those different optimizers? We will also be covering different activation functions, which are really important, and we'll be covering them in detail to also understand the concept of saturation, how this is causing vanishing gradient problem. And also we'll be covering the different aspects of just the entire training and testing process behind neural networks. And then we will move towards more complex topics, and those will be the next 10 questions. So we will be covering the concept of backpropagation in more detail, the relationship with the gradient descent, and we'll be covering the vanishing as well as the exploding gradient problem. We will also be covering various question-specific and problems related to deep learning models that you will be asked during your interviews. We will also be covering the loss function and various type of popular loss functions that you can expect questions about during your deep learning interviews. In the next 10 questions, we will be covering the following 10 questions. So we will be covering the SGD algorithm, so more advanced version of GD. We will be covering the SGD with momentum. What is the role of this momentum? We will also be covering the different versions and variants of GD, something that comes time and time again during the deep learning interviews, such as the batch GD, minibatch GD, and the SGD. What is the difference between them? What is the function of batch size? Another very popular question you can expect. We are also going to cover the idea of Hessian, how Hessian is being used as part of different optimization algorithms. Also, what is the RMSProp and what is the infamous Adam algorithm. Then, as part of the next 10 questions, we will be covering a bit more complex topics. We will be covering the concept of AdamW, and then we'll be covering the batch normalization, what is the difference between batch and layer normalization, how layer normalizations are used as part of transformers, what is the residual connection, what is the function of residual connections, and we'll also be talking about gradient clipping, Xavier Initialization, as well as the ways that we can solve vanishing gradient problem and the exploding gradient problem. Then we will also be covering the concept of overfitting, definitely something that you can expect during your deep learning interviews. Then as part of the final 10 questions of this part of the course, we will be covering the concept of dropout and the regularization in neural networks. We will be covering the overfitting problem and how it can be solved in neural networks. Also, what is the difference between dropout and random forest? So different tricky questions that you can expect that have the goal to confuse you, but we will clear out everything such that you don't need to confuse anything during your interviews. And then we'll be covering the concept of the training versus testing, the adjustment when it comes to dropout. We'll be covering the L1 regularization, L2 regularization, what is the difference between them, and the impact on the weights, the penalization impact, and the difference, how severe they impact the moral performance. We'll also be covering the concept of curse of dimensionality and how deep learning is solving this problem. Then we will be covering the concept of generative models. Honestly, more and more people are getting into deep learning. So whenever you want to get into AI or in machine learning, you just want to start from the fundamentals. And to understand those more complex models such as transformers, GPT series, T5, in order to understand those mechanisms, you need to know the basics. And those are the deep learning fundamentals, something that we are going to cover as part of this course. Because once you know the fundamentals, then you will also be prepared to answer more advanced questions and also to be able to answer the follow-up questions. Because during the deep learning interviews, you are not only going to answer the questions quickly and in a scripted way, but you will most likely get those follow-up questions. And I'm going to help you with my detailed explanations in such a way that you will not only be prepared to ace those basic questions, but also the corresponding follow-up, more advanced questions. Do note that the idea of this course is not to learn all the concepts from scratch, but instead to either quickly refresh your memory from deep learning or to prepare for your deep learning interviews, and you already know the most of these concepts. There are quite a lot of complex topics that we will be covering as part of deep learning, and I would suggest you to first refresh your memory when it comes to statistics, machine learning, and also various type of mathematical concepts such as the matrix multiplication with linear algebra, differentiation theory, and then get into this interview preparation course. When it comes to the fundamentals to statistics, if you want to refresh your memory in this topic before getting into this course, I will put a link that will forward you to the fundamentals to statistics course as part of LunarTech, where you will be able to learn the statistical concepts or refresh your memory. And when it comes to machine learning, my Fundamentals to Machine Learning handbook from freeCodeCamp or Fundamentals to Machine Learning course as part of LunarTech Bootcamp will be able to help you to either learn or refresh your machine learning memory. And once you have done that all, then you are ready to conquer your deep learning interviews. I hope you guys will stick around because this course is going to be very helpful for anyone who wants to prepare for deep learning interviews. So if you're ready, I'm really excited. So let's get started. So the first question is, what is deep learning? So in this question, your interviewer wants to understand whether you have an understanding where the deep learning comes in comparison to machine learning, in comparison to AI, and you can briefly mention about the idea of neural networks and how it is related to human brain. So deep learning is a subset of machine learning, which is then a subset of AI, so a branch of artificial intelligence, which involves training artificial neural networks on large amount of data in order to identify and learn those hidden patterns, nonlinear relationships in the data, which is something that the traditional machine learning models like linear regression or logistic regression or random forest and XGBoost are not doing so well as the deep learning models. And the heart of deep learning is the concept of layers, because the artificial neural networks and just in general, the deep learning tries to replicate the way human brains work and the way we intercept and take the input signals from outside world when we see something or hear something or smell something, and then use that information in order to learn and in order to whether to make conclusions or to do something. And that's exactly what deep learning tries to do. It tries to use this idea of neural networks, which are deep learning models, in order to take the input data in the input layer and then transform this through the activation functions to activate these neurons and then transform it into activations. And this will be in our hidden layers. And the magic happens in the deep learning model to identify the nonlinear relationships in the input data. And then what it does is that it produces then the output. So this is at a very high level. The interviewer doesn't want you to explain the idea of weights, the idea of parameters, which we will talk about later. But then the interviewer wants to know whether you have high level understanding what this deep learning is, and maybe also to give you examples of deep learning models. Definitely mention this relationship between the way the human brains and the neural networks. You specify this idea of input data, input signals and activations and hidden layer. Don't go too much into detail of the architecture of neural networks, and do briefly mention that these deep learning models, examples of deep learning models are, for instance, artificial neural networks, recurrent neural networks, LSTMs, the different sorts of more advanced architectures such as variational autoencoders. They are also based on neural networks. You get the idea. So if I were to answer this question very short, I would just say that deep learning models are a subset of machine learning models on its turn, a branch of artificial intelligence that tries to learn complex data and large amount of data and discover hidden patterns and complex structure in this pattern for various type of tasks, including computer vision, including machine translation tasks, a lot of NLP models, the infamous ChatGPT, so GPT models or T5, all these large language models, they are all based on neural networks and they are deep learning models. So the next question is, how does deep learning differ from the traditional machine learning models? Here, your interviewer wants to understand whether you know what are the main advantages of the deep learning models compared to machine learning models. So do mention a few examples of traditional machine learning models, and then mention a few examples of deep learning models, and try to put the focus on one or two advantages of the deep learning models. So a few examples of machine learning models are linear regression, logistic regression, the support vector machines, naive Bayesian algorithm, k-means or clustering, so as an unsupervised learning model, dbScan. Do mention few boosting algorithms such as GBM, XGBoost. So you can also mention random forest, very popular for regression as well as classification type of tasks. So in this way, you will show to your interviewer that you know quite well those machine learning algorithms. Then do mention the deep learning models, which fundamentally differ from the machine learning models, and mention examples such as ANNs, RNNs, LSTs, GRUs, and autoencoders, all based on neural networks. Do also mention CNNs, so convolutional neural networks, very much popular in the field of computer vision. Then do point out that the first biggest difference is that traditional machine learning models, they rely on manual feature extraction, while deep learning models, they do this automatically. And they automatically take the input data as it is. We don't need to perform feature selection. We don't need to worry about that because our model, represented by neural networks, especially with these deep layers, is able to identify these patterns in all this data and then extract for itself the most important features that describe our data. And then use it for different type of tasks, whether it's for regression, for classification. It actually performs very well. So deep learning models perform very well on big data, something that we have seen machine learning models suffer. So ML models are known for becoming worse in terms of their performance when the size of the data increases, when the number of features increases, they start to overfit and they start also to become unstable and not accurately predict the output when we increase the number of observations in our data, also include complex features in the data. That's something that definitely helped the deep learning models outperform the traditional machine learning models, especially in the tasks such as computer vision or speech recognition, machine translation. And the idea of deep learning models, you can even see why they are better than machine learning models by even looking at the most recent different sorts of applications across different tech fields. You can see that most of them are based on some sort of neural network based algorithm rather than machine learning models. And this is mainly because of these various abilities of deep learning models, including ability to handle large data, ability to handle complex features, and being able to do feature extraction on itself instead of doing it outside of the model or instead of suffering from various type of problems like the traditional machine learning models do. So the next question is, what is a neural network? So here your interviewer wants to understand the relationship between the neural networks to the human learning, the way we learn, and whether you know these components and how the components flow. So in terms of the training process, whether you know what the weights are, what the parameters are, whether you know what these hidden layers are, whether they are just one or multiple. You understand the concept of deep neural networks and how this flow of information happens, and whether you mention all these elements of the neural networks. So I would mention as an answer to this question that neural networks is a foundational concept in the field of deep learning and in the field of artificial intelligence just in general. And it's a computational model that is inspired by biological human brains. And it tries to replicate the way humans learn, the way they interpret information. They take the input data and they process that information. So they do the training of the on the input data, and they also consistently update on this information. So they learn something new, they add new information, and then they update the possible outcome. And the end result is to minimize the amount of error we are making when we are learning. And that's exactly what we are doing in neural networks. So the core of neural network is made up of these units, which we are calling neurons, like in our human brains. And these neurons are together forming the layers. We have input layer, which represents our input data. Then we have the weights, which showcase how much importance we need to put on different input signals. And these weights are what we are calling parameter in our model, which we need to consistently update when we are performing the training, so the learning process. So these layers include the input layer, one or more hidden layers, which is the middle part of our neural network, and that helps to learn these different patterns, helps to understand, activate certain neurons and deactivate or activate less the other input neurons, and then transforms this information. After these activations are done, we go through this hidden layer, and after this hidden layer, then we can have another hidden layer, which will then receive the information from the previous hidden layer and will then continue the learning process. On its turn, it will be able to learn and understand the previous hidden layers information. And as an example of this process, think of that in the input, we have the different pixels of the images, and we want to learn these images. And for the model, for the neural network to learn, it should be able to first learn some sort of objects in the input data. So in the first hidden layer, it might discover certain signals, certain edges, and certain information. And then in the next hidden layer, it will be able to identify specific objects. For instance, the ears of a cat, if we want to identify what the image is of a cat or a dog, and then passes this information onto the next layer, and then we go on to the final layer when we produce the output. Now, if you are familiar with machine learning and if you are looking at this tutorial, I assume that you are familiar with the idea of classification, regression, unsupervised learning, supervised learning. So in case of the traditional neural networks, we then produce the output. And it can be, for instance, identifying a probability, a value between 0 and 1, let's say for our classification task. And then this value should be compared to the actual class. So if we have, for instance, probability and we transform it to the class, then we can update the corresponding, so we have the output of our neural network in each epoch. And then we use this information to compare to the true labels in our supervised learning process. And then we compute the error. So we are trying to understand how well we did our prediction. And then this information is being used to then understand how accurately is the model predicting the results. And this is what we are calling loss. So this loss function is then used in order to understand how much we need to change the weights, so how much importance we put on the neurons, how much we need to update these weights as well as the other parameters in our model in order to reduce the amount of error our model is making. And that's the underlying idea of neural networks, to take the input, put it through those hidden layers to learn from this input data, activate the neurons, and have either one hidden layer or multiple hidden layers, continuously activate those neurons, get the output, understand what is the loss that our model is making, the overall cost function, and then compute what we are calling gradients. And do briefly mention here the idea of gradients, but do not go too much into detail of it. And then using these gradients, we understand how much we need to update these weights in order to improve our parameters of our model. Because at the end of the day, what we care about for our final result is this model that has the parameters, the weight parameters, the bias parameters that will end up generating the most accurate predictions for us. And for that, we need to continuously go through this loop in order to properly learn and in order to produce a model that makes the minimum amount of error. So it's able to properly learn from the input data. The next question is, explain the concept of a neuron in deep learning. In this question, the interviewer wants to hear about the concept of weights, the concept of bias factors, how they are used in order to obtain the so-called z-scores, and how the activation functions are used to obtain activations, and what is the point of these weights and the bias factors and relationship to the learning process. So a neuron in a deep learning, it is sometimes referred as artificial neuron, which mimics the function of the human brain's neuron. But it does so in a mathematic and simple way. And the idea is that in a neural network, the model gets different inputs. And here, these input signals we are calling neurons. It takes the input data, which we represent and call it as an X, and we use this X to multiply it by weights, because these weights can then tell us how much importance this neuron should have, how much attention we need to pay to this neuron. And these weights are then multiplied by this input data, which we call X, those are the neurons, and we add a bias factor, because there can be always a bias introduced when we are performing our learning process. And the weights multiplied by this input data X, we are adding then on the top of that the bias factors, and this will be our z-scores. But then in the next stage, before approaching the hidden layer, we use what we are calling activation functions. And activation function, such as sigmoid function, rectifier linear unit, or leaky ReLU, all these activation functions, what they are doing is that they are mathematically introducing nonlinearity into our neural network. And these activation functions are applied to all these different z-scores, which is based on the weights and then the input data and bias factors, in order to understand how much each neuron should be activated. It can be that we want, when looking at the object and trying to understand what is the object in that image based on the pixels, it can be that we need to activate certain neurons related to that specific area or that specific object, and we should not activate the other neurons. And that's exactly what we are doing with these activations of these neurons. So Here then we are using these activations to introduce nonlinearity for the neural network to learn these complex structures in the input data. So the next question is, explain architecture of neural networks in simple way. Given that we have already answered the previous questions, all mentioning some parts of the architecture and the training process of neural networks, this one will be easy to answer, and I will use here a simple visualization for simple neural networks that consists of just one hidden layer to just summarize everything that we mentioned as part of previous interview questions. So the neural network is this multi-layer structured model, and each layer is transforming the input data step by step. Think of it like an assembly line, where every stage adds more complexity on the previous stage. And the detail and the complexity is adding more value to the ability of the model to perform predictions. So in the beginning, the model has these input layers. As you can see here, the input layers are represented by this Z1, Z2, Z3 up until Zn. And in here, you can think of these elements, these inputs as part of input layer as features describing the data. So it can be, for instance, that we want to use neural network to estimate the price of a house. We need to have certain features to estimate that price. We need to learn and in order to understand how we can differentiate different houses and how these features influence the house price. So Z1 can be, for instance, the number of bedrooms of this house. Z2 can be the number of levels of this house. Z3 can be whether the house has a swimming pool or not. Another feature can be whether the house was built. So what is the year that the house was built? What is the age of the house? All these features, they describe a certain element or certain characteristic of the house. And this will help us and this will help the model to learn from this feature and to understand what will be possible accurate price for this house. And then we have these different weights. As you can see, we have weight 1, weight 2, weight 3, and then we have the corresponding weights for the second input, the corresponding weights for our third feature, so corresponding to the Z3, such as W31, W32, and W33, etc. As you can see, these weights, they show a pile that goes, an arrow that goes onto the next layer, which is our hidden layer. So in this simple architecture, we got just one hidden layer, but it can also be that you have more hidden layers, which is usually the case with the traditional deep neural networks. Hence also the name deep. So what these weights do is that they help us to understand how much this input feature should contribute to first hidden unit, second hidden unit, and third hidden unit. So as you can see, in our hidden layer, we have these 3 circles. These 3 circles describe the hidden units in our hidden layer. And we have the simple structure, so we got just 3 hidden units. But this is something that you can decide for yourself when training your model. It's also what we are calling hyperparameter that you can tune. So in here that you can see that the W11 goes from Z1 to H1. So this is the importance weights that tell to the neural network how much the input layer should get attention, when should get importance, when it helps you learn the first hidden unit. So for H1, what is the weight that we need to put on Z1? So our first feature. Then we have the W12, which describes the amount of weights that we need to put on the first input feature when identifying this, when learning and putting the information into our second hidden unit, H2. So you get the idea. So then this weights and the corresponding bias factors and the input data helps us to compute what we are calling z-scores. And z-scores, so z can be represented as the w, so the weight, multiplied by x, which is the previous, in this case, the input data, plus bias vector, which we sometimes refer as b. Then once we have the z-scores, we are then ready to add a nonlinearity, so the activations, which will then help us to understand how we need to perform aggregation. So you can see that when it comes to the first hidden unit H1, there are 4 different piles, so arrows that comes to H1. It is the W11, W21, W31, and WN1. What this basically means is that we have this different input features, and per input feature, we have the corresponding weight that helps us to understand how much attention we need to pay on these different input features when we are obtaining the H1. So our hidden layers, first hidden unit. And we can aggregate these different z-scores that we compute based on different weights, different input signals, and this activation function can significantly change on the way we calculate our activations in the H1. And that's exactly what the activation does, so the activation functions. Then once we have this information, we have computed our activation, we are ready to compute our output. And the output is done after we have computed our H1, H2, and H3. Those hidden units have learned based on the weights and the bias factors and the activation function, the information in our input data in the previous layer. Then we use the final weights, so WH1, WH2, WH3, in order to understand how much each hidden unit need to contribute to the output layer. And in this output layer, what we are doing is that we are getting the output in the format that is desired. So it can be that we are performing classification and we want to get a probability. Therefore, we need to obtain a value between 0 and 1. Then in this output layer, we will then have this value, we will transform it to a class, and we will compare it to the true labels such as zeros and ones to understand how well our simple neural network is performing. So the next question is, what is an activation function in neural networks? So activation function in neural network plays a crucial role, and the choice of activation function will define the performance of your neural network. We by now have already spoken a lot about the weights and how we compute the z-scores using the weights, the input data, or the previous layer's input, previous layer's output. We add the bias factors to obtain the z-scores, and then we need to apply activation function to obtain the activation. So how much each neuron should be activated when computing the next layer. So that is exactly what activations do. So activation functions, they in neural network, they introduce the idea of nonlinearity. If we were to not use specific type of activation functions, our model will be similar to the linear regression model. We will have a plain linear type of model that will be able to uncover the linear patterns and will not be able to discover these complex hidden patterns in the data. And we have seen that in the true world, the data most of the time contains nonlinear relationships. Therefore, we introduce the activation functions, which help us to introduce nonlinearity into our neural network. And they are like aggregation functions that help us to understand how we need to combine these different these different neurons corresponding z-scores in order to obtain final, single activation value. So in here, if you look at this figure, you can see that we are using the x1, x2 up until xn, which are our input points. And then we have the corresponding weights, which tell us how much each of these inputs need to be activated. And then we need to aggregate these values. We need to obtain one single activation, which will be then based on the activation function. It basically defines how much we need to add a value that corresponds to that specific input when computing the hidden units value that we saw before. And there are different sorts of activation functions. Do mention briefly that the four popular activation functions are sigmoid activation function, the hyperbolic tank function, which shortly is referred as tank function. Also definitely mention about rectifier linear unit activation function, so the ReLU, and also mention the leaky ReLU, so the leaky version of the rectifier linear unit activation function. You can also, if you have time, you can also specify that activation functions, they act like a gatekeepers. So they decide how much information needs to be used from this state to be passed onto the next state. So that's basically the idea behind activation functions, which enable the neural networks to properly learn nonlinear relationships in the data. The next question is, name few popular activation functions and describe them. So we briefly spoke about activation functions in the question number 6. So here I will go into much more detail about these different activation functions, and we'll also make a categorization between them. When you are getting asked this question, you don't need to give all these different sorts of examples, just one example out of these 4, and then provide this detailed explanation of this specific activation function. But in this case, what I would do is that I will provide you all four popular activation functions largely used in the industry, and then it will be up to you to decide which one you will give as an example. So I tend to make this categorization behind these 4 activation functions. So sigmoid activation function, tank activation function, rectifier linear unit or short ReLU activation function, and the leaky rectifier linear unit ReLU activation function. So I tend to say that sigmoid function and tank function, they can form a single category. And then the rectifier linear unit and its adjusted version, leaky ReLU, they can form the second category of activation functions. And we will soon see why. So let's now start with the sigmoid activation function. So if you are familiar with the logistic regression, then you most likely will recognize this activation function, because sigmoid function is also used in logistic regression when we are trying to produce values that are like probabilities, so values between 0 and 1. So as you can see, in case of sigmoid activation function, we are getting this S-shaped curve when it comes to the diagram that describes the activation functions. And so what goes into activation function? We are computing the z-scores, which are then based on the previous layer's data, so output. It can be, for instance, described by x, and then we are multiplying this x by the weights, let's say w, and then we are adding bias factor, let's say b, and then this helps us to get the z-scores. Then the z-scores needs to be used and given us an input into the activation function. And this is exactly then what transforms the z-scores into activation function. And in here, it is the sigmoid activation function. So sigmoid activation function then takes the input, let's say z, and then what it does is that it transforms into this value, where the value is 1 divided to 1 plus e to the power minus z. So similar to what we do in logistic regression. And as you can see, what this graph represents, which is a sigmoid function, in the x-axis, we have all the z-scores, basically, and in the y-axis, we have the corresponding activations. And you can see that for all the values from minus infinity till plus infinity for the x's, so for the z-scores, the corresponding activations, so on the y-axis, we have values between 0 and 1. So the minimum is 0 and the maximum is 1. So you can see that the inflation point, so the point where we go when we flip the curve, is at 0.5. And this activation function, you can see that whenever we have a negative values, then the corresponding activations will be between 0 and 0.5. It is all these areas. And whenever we have the z-scores, which are positive scores, the corresponding, so if we have positive scores for our z-scores, then the corresponding activations will be between 0.5 and then 1. What is really important to remember and mention during your answer as part of the interview question is that sigmoid function is suffering from what we call saturation. So what is saturation? So saturation happens when we take a very large negative values or very large positive values, then the activation or the value, in this case of a function, converges to the extremes of the corresponding function. And this is exactly what happens here. If we look here, if we take, let's say, the x equals to minus 1000, then the corresponding y will be most likely very close to 0, and which is the minimum, so it's the extreme of this activation function. And if we take the x as a very large positive number, like plus 1000, then the corresponding activation value will be very close to 1, which is then the global maximum of this function. So this is exactly what we refer as saturation. So it means that if we take very large negative or very large positive number for our z-scores, this activation function will then provide us an output, a value that is very close to the extremes, so two extremes, the 0 and the 1 of the corresponding activation function. And later on, we will see why this can be problematic if we use this function as part of our activations for the hidden layers. But of course, when it comes to getting a value, an output between 0 and 1, which is exactly what the sigmoid function is doing, then the sigmoid function would be the go-to activation function. So the next activation function that we will talk about is the hyperbolic tank activation function, in short, tank function. So as you can see, the hyperbolic tank function is quite similar in its shape to the sigmoid activation function. Only what it does different is that it transforms all the values to value between minus 1 and 1 instead of 0 and 1 like the sigmoid function was doing. So the tank function, as the name suggests, it's based on the idea that comes from geometric topics. If you are familiar with the idea of sinus, cosinus, tangent, and cotangent, then this will be familiar to you because this function does exactly that. So it uses this tank function to transform all the z-scores to value that is between minus 1 and 1. So the fz, which represents this activation function, is a function that is equal to, in the denominator, we have e to the power z minus e to the power minus z divided to e to the power z plus e to the power minus z. So what it basically does is that it transforms, it takes the z-scores, and if the z-scores are negative, it transforms it to the values between minus 1 and 0. And then if the z-scores are positive numbers from 0 till plus infinity, then the corresponding activations will be between 0 and 1. And as in case of sigmoid function, tank function also is S-shaped. Only the inflation point, so the point where it changes its pattern, the way the graph behaves, is not at the point 0.5, but it's at the point of 0. Like sigmoid function, tank function also suffers from saturation. So for large negative and large positive numbers, the corresponding activations will be very close to the extreme point, so the minus 1 and plus 1. For this function, which can be problematic, like in case of sigmoid function. So don't use these two functions for your hidden layers, but use them for the output layer. And we use them for the output layer simply because the value that we are getting from these two functions is very convenient to transform it to the corresponding value, whether it's, for instance, classification case, because if we get a value between 0 and 1, for instance, as in case of sigmoid activation function, then we can interpret this as probability, and this probability can be then used for getting a class, so class 0 and 1, for instance, and this then can be used for evaluating our model by comparing it to the actual classes and compute the cross entropy or any other evaluation metrics can be computed based on this. And later on, we will see why these two activation functions should not be actually used in the hidden layers, especially for deep neural networks that have many hidden layers. But for now, as this is out of the scope of this question, I don't want to go into details as we have already covered quite a lot. So the next two activation functions that you can mention when answering this question can be the rectifier linear unit and the leaky rectifier linear unit activation functions. The two are very similar, especially when it comes to the positive z-scores, but they are a bit different when it comes to the negative z-scores. So what do I mean by this? When we look at the rectifier linear unit, so ReLU activation function, you can see that it looks like this. So it takes for all the cases when the Z, so the activation, if the z-score is smaller than 0, so it's a negative number, then the corresponding activation will be 0. So basically, this activation function will not be activating any of the negative neurons. Whereas for the cases when we have the z-scores positive, then the corresponding activations will be exactly equal to the z-scores. So hence the name linear. So if you look at the y is equal to x line and you visualize that line, you can see that the positive part, so for the part where the x is positive from 0 till plus infinity, you can see that y is equal to x line is exactly like that, exactly what we have here. And that's where the name linear comes from. So it's like the linear function representation. But this only holds for the positive numbers. So for positive numbers, we will get the z-scores and we will activate them by their exact amount. Whereas in case of negative z-scores, so negative neurons, then the corresponding activation will not happen and we will not be activating these negative values. And for all these cases, the activation function will set the activation equal to 0. So this can be problematic for the cases when we do want to have the output, we do want to take into account these negative values, and we want to consider these negative values and perform the predictions based on them too. In those cases, we need to adjust this ReLU. So we can then better use what we are calling leaky ReLU. And what this leaky ReLU activation function does is that it not only activates the positive scores, but it also activates the negative ones. It does that at a lesser extreme than for the cases when dz is positive, of course, as you can see from this negative side. So from this third quarter of our graph, but it still does it. And you can see it also from the function itself, because the activation function corresponding to leaky ReLU can be represented by this f set, which is equal to 0.01 if z is smaller than 0, and is equal to z if z is larger than or equals 0. So for all the positive numbers, the leaky ReLU acts exactly the same as for ReLU, as you can see here. But for the negative values, the corresponding activation is simply equal to 0.01. So you can see that it is this part of the figure. So both of these activation functions do not suffer from saturation, something that is definitely different compared to the sigmoid and tank function. And that's why it is recommended, and it has been proven, that these two activation functions perform much better when we use them as part of our hidden layers activations, and they are not so much used when it comes to output layer. So think of like using the leaky ReLU and ReLU for your hidden layers, but not to use them for your output layer, and the other way around for the sigmoid function and tank function. Use them for your output layer, but not for your hidden layers. So the next question is, what happens if you do not use any activation functions in a neural network? So the answer for this question can be very short because it is quite obvious. So the absence of activation functions will reduce the neural network to a common machine learning model like linear regression, something that removes the entire idea of using neural networks in the first place. Therefore, in order to be able to utilize the architecture of neural networks and to be able to discover hidden patterns in our data, nonlinear patterns, we can use the activation functions and nonlinear activation function. The next question is, describe how training of basic neural networks work. So in this case, your interviewer wants to know whether you know the idea of a forward pass, backward pass, what is backpropagation, how these processes are connected to each other, and how neural networks utilize these layers in order to learn these complex patterns in your data. So you can start by describing the training process of neural network, a very basic one, by the process of what we are calling forward pass. Forward pass takes the input data and processes through neurons, which we saw before, and uses this weighted sum and activation functions to produce an output. So we take the input data, we multiply it by the corresponding weights, and then we add a bias factor. Then those are our z-scores. Then we apply an activation function to introduce nonlinearity. And these activated values, the activation scores, then are used when we are passing information onto the next layer, because then we are using this as our input, we are multiplying it by the corresponding weights, we are adding the bias factors, and then we are using activation function for that hidden layer in order to learn from these complexities. This process continues until we reach the output layer where we compute our output. So this output is then used to compare it to the true values that we have for our data. So it can be, for instance, the true labels of our observations in a classification problem. Then we compute what we are calling a loss function or a cost function. It can be, for instance, the RMSC or MSC for a regression type of problem. It can be, for instance, cross entropy for classification type of problem. And then using this loss function, we are then doing what we are calling backpropagation. Backpropagation is then the process of computing the gradient, so the first order derivative of this loss function with respect to the weights and the bias factor. So with respect to the parameters of our model that we want to improve. And once we have computed this gradient, which tell us how much our loss function will change if we make a certain change to our weights and to our parameters, so the bias factors, then we can use these gradients in order to update our parameters in our model. And the way we are doing that is by the process of backward pass. So this is the opposite of what we are doing in the forward pass. In the forward pass, we go from left to the right till the end of the model to get the output. In the backward pass, we do the opposite. So we are going backwards. We have identified the gradients by doing backpropagation. Then we are using these gradients, we are giving it as an input to an optimization technique. It can be SGD, GD, SGD with momentum, RMSProp, Adam, you name it. And then using that approach in order to update our weights and our bias factors layer by layer. So then what we are basically doing is that we are taking the gradients, we are taking the optimization algorithm that we will use, let's say Adam, and then we are updating the weights corresponding to the last layer. We have computed that, then we go on to the next layer that comes before. So in this way, we go from very deep layers to the left one. So from using the multiplications between the weights. And in this way, we are then using the gradients and we are updating the weights and the bias factors in such a way that we can adjust the weights and then reduce the loss function. So this is very important to mention and to show the interviewer that you understand why we are updating the weights and why we are updating the bias factors. Because mathematically, the gradients show how much change will be in the loss function when we change a certain weight or certain bias factor by a certain amount. It can be small amount. And that is something that we are using, the gradients, in order to update the previous weight parameters and the bias parameters such that we can reduce the loss that our model is making, because this will mean that we are one step closer to having more accurate model. The smaller amount of error we are making, the smaller is our loss, the better is our neural network performing. So that's the idea behind training of the neural networks. And this process continues on and on. We have forward pass, backpropagation, backward pass, and on until we have reached some sort of end criteria, so stopping criteria, let's say the number of iterations, number of epochs, or some other stopping criteria. The next question is, what is gradient descent? So gradient descent is an optimization algorithm that we are using in both machine learning and in deep learning in order to minimize the loss function of our model, which means that we are iteratively improving the model parameters in order to minimize the cost function and to end up with a set of model parameters that will optimize our model. And the model will be producing highly accurate predictions. So in order to understand the gradient descent, we need to understand what is the loss function, what is the cost function, which is another way of referring to the loss function. We need to also understand the flow of neural network, how the training process works, which we have seen as part of the previous questions. And then we need to understand the idea of iteratively improving the model and why we are doing that. So let's start from the very beginning. So we have just learned that during the training process of a neural network, we first do the forward pass, which means that we are iteratively computing our activations. So we are taking our input data, we then are passing it with the corresponding weight parameters and the bias vectors through the hidden layers, and we are activating those neurons by using activation functions. And then we are going through those multiple hidden layers up until we end up with computing the output for that specific forward pass. So the predictions, y hat. So once we perform this for our very initial iteration of training the neural network, we need to have a set of model parameters that we can start training process in the first place. So we therefore need to initialize those parameters in our model. And we have specifically two types of model parameters in the neural network. We have the weights and we have the bias factors, as we have seen in the previous questions. So then the question is, well, how much error are we making if we are using this specific set of weights and the bias factors? Because those are the parameters that we can change in order to improve the accuracy of our model. So then the question is, well, if we use this very initial version of the model parameters, so the weights and the bias factors, and we compute the output, so the y hat, then we need to understand how much error is the model making based on this set of model parameters. That's the loss function. So loss function or the cost function, which means the average error that we are making when we are using these weights and the bias factors in order to perform the predictions. And as you know already from the machine learning, we have regression type of tasks and classification type of tasks. Based on the problem that you are solving, you can also decide what kind of loss functions you will be using in order to measure how well your model is doing. And the idea behind neural network training process is that you want to iteratively improve this model parameters, so the weights and the bias factors, such that you will end up with the set of best and most optimal weights and the bias factors that will result in the smallest amount of error that the model is making, which means that you came up with an algorithm and with neural network that is producing highly accurate predictions, which is our goal, our entire goal by using neural networks. So loss functions, if you are dealing with classification type of problems, can be the Cross Entropy, which is usually the go-to choice when it comes to the classification type of tasks. But you can also use the F1 score, so F beta score. You can use the precision, recall. Beside this, in case you have regression type of task, you can also use the mean squared error, the MSE. You can use the RMSE, you can use the MAA. And those are all the ways that you can measure the performance of your model every time when you are changing your model parameters. So we have also seen as part of the training of neural network that there is one fundamental algorithm that we need to use, which we called and referred as a backpropagation, that we use in order to understand how much is there a change in our loss function when we apply a small change in our parameters. So this is what we were referring as gradients, and this came from mathematics. And as part of the backprop, what we were doing is that we were computing the first order partial derivative of the loss function with respect to each of our model parameters in order to understand how much we can change each of those parameters in order to decrease our loss function. So then the question is how exactly gradient descent is performing the optimization. So the gradient descent is using the entire training data when going through one pass and one iteration as part of the training process. So for each update of the parameters, so every time it wants to update the weight factors and the bias factors, it is using the entire training data, which means that in one go, in one forward pass, we are using all the training observations in order to compute our predictions and then compute our loss function and then perform backpropagation, compute our first order derivative of the loss function with respect to each of those model parameters, and then use that in order to update those parameters. So the way that the GD is performing the optimization and updating the model parameters is taking the output of the backprop, which is the first order partial derivative of the loss function with respect to the model parameters, and then multiplying it by the learning rate or the step size, and then subtracting this amount from the original and current model parameters in order to get the updated version of the model parameters. So as you can see here, this comes from the previously showcased simple example from neural network. And here, when we compute the predictions, we take the gradients from the backprop, and then we are using this dv, which is the first order gradient of the loss function with respect to the weight parameter, and then multiply this with the step size, the eta, and then we are subtracting this from v, which is the current weight parameter, in order to get the new updated weight parameter. And the same we also do for our second parameter, which is the bias factor. So one thing you can see here is that we are using this step size, the learning rate, which can be also considered a separate topic. We can go into details behind this. But for now, think of the learning rate as a step size, which decides how much of this size of the step should be when we are performing the updates. Because we know exactly how much the change there will be in the loss function when we make a certain change in our parameters. So we know the gradient size, and then it's up to us to understand how much of this entire change we need to apply. So do we want to make a big jump, or we want to make a smaller jumps when it comes to iteratively improving the model parameters? If we take this learning rate very large, it means that we will apply a bigger change, which means the algorithm will make a bigger step when it comes to moving towards the global optimum. And later on, we will also see that it might become problematic when we are making too big of a jumps, especially if those are not accurate jumps. So we need to therefore ensure that we optimize this learning parameter, which is a hyperparameter, and we can tune this in order to find the best learning rate that will be minimizing the loss function and will be optimizing our neural network. And when it comes to the gradient descent, the quality of this algorithm is very high. It is known as a good optimizer because it's using the entire training data when performing the gradient, so performing the backprop and then taking this in order to update the model parameters. And the gradients that we got based on the entire training data is the represents the true gradients. So we are not estimating it, we are not making an error, but instead we are using the entire training data when calculating those gradients, which means that we have a good optimizer that will be able to make accurate steps towards finding the global optimum. Therefore, GD is also known as a good optimizer and is able to find with higher likelihood the global optimum of the loss function. So the problem of the gradient descent is that when it is using the entire training data for every time updating the model parameters, it is just sometimes computationally not feasible or super expensive. because training a lot of observations, taking the entire training data to perform just one update in your model parameters, and every time storing that large data into the memory, performing those iterations on this large data, it means that when you have a very large data, using this algorithm might take hours to optimize, in some cases even days or years, when it comes to using very large data or using very complex data. Therefore, GD is known to be a good optimizer, but in some cases it's just not feasible to use it because it's just not efficient. The next question is, what is the role of optimizer in deep learning? So when it comes to training a neural network, we want to find what is the set of hyperparameters and what is the set of parameters that we can use as part of our model that will end up making the least amount of error. Because when our algorithm is making the smallest amount of error, it means that our predictions are most likely accurate. And when using it on a new unseen data, it will also perform in a much better way. So it means that we can rely on this algorithm and we can apply it across different applications without worrying that it's making too much of an error. So in order to perform this optimization, we are making use of different optimization algorithms. Gradient descent that we just discussed is one of such algorithms that is used in order to update the model parameters in order to minimize the amount of error that the model is making. In this case, the amount of cost or the loss that the model is making by minimizing the loss function. So that is basically the primary goal of the optimizers in not only deep learning, but also in general in machine learning and in deep learning models. So the idea is that we will iteratively adjust the model parameters, in this case the weight parameters and the bias parameters in our model, in order to end up with the scenario and with the model where the algorithm is making the minimum amount of error. Or in some cases, it can be if the objective function is of the nature that should be maximized, it means that we will need to come up with a set of parameters of the model that will maximize that objective function. So depending on the type of objective that you have as part of your algorithm, you will need to then decide how your optimization algorithm should be applied. You will need to minimize or you will need to maximize your objective function. So when it comes to the optimization algorithms, we have the very original optimization algorithms, but there are also many other variants of GD that have been developed over the years in order to combat some of the disadvantages that the GD has, but at the same time also to try to replicate the benefits of the gradient descent. So the SGD is one example of optimization algorithm beside of GD. There is this minibatch GD. We also have SGD with momentum when the momentum was introduced to improve the optimization algorithms such as SGD. We also have adaptive learning based type of optimization techniques such as RMSProp, Adam and AdamW, also AdaGrad, and those are all different sorts of optimization algorithms that are used in deep learning in order to optimize the algorithm. So another aspect that we need to keep in mind is that the goal of the optimization algorithm is to iteratively improve the model parameters such that at the end we will end up finding the global optimum. So during the various type of explanations when explaining the variance of gradient descent and other optimizers, I will be continuously making use of this term global optimum. So what global optimum means is that it is the actual minimum or actual maximum of the objective function that we are using to measure the error that the model is making. Because we can have a local minimum or local maximum versus global minimum or global maximum. What this means is that when we have this area consisting of many values that the error can take, in some cases, when the optimization is making those movements in order to reach that minimum, it might confuse and end up discovering the local minimum or local maximum instead of finding the global minimum and global maximum. What this means is that for some area, when the optimization algorithm is moving in order to understand how it should improve its direction to identify that minimum, in some cases it might discover that, well, this is the minimum that we are looking. So the algorithm will converge and it will decide that this is the set of hyperparameters and parameters that we need to use in order to optimize our model. But in the reality, it has confused the global minimum with the local minimum, and it has falsely declared that the algorithm has converged and it has found the actual minimum. But it is actually the local minimum, not the global one. And global minimum, it means that it is actually the minimum, because the local minimum can seem as if it is the minimum of the loss function, but actually it is just a value that it is much smaller than the surrounding values, but it's actually not the smallest one in the entire set of values. So ideally, we want to end up with a convergence and with a state of the model where all the weights and the bias factors we found, they result in the actual minimum of the loss function, and not just a value that for a certain set of values seems the minimum. Therefore, the goal is to identify the global minimum and not the local one. Next question is, what is backpropagation and why it is important in deep learning? So backpropagation is a fundamental and essential part of training of a neural network. It helps you learn from the errors that the model is making in each iteration in order to understand how the change in the certain parameters of the model, such as weight factors and bias factors, will result in a change in the loss function. So the backpropagation algorithm is the middle part of the entire training process. And what I mean here is that we first perform our forward pass. We go through all this transformation when feeding the input data into our network. And then based on these transformations, we then end up with the final output layer, and we then can perform our prediction. So we compute the y-hat. Once the y-hat is computed, we can then compute the loss function for that one specific iteration after that forward pass. Once we have the loss function, then we can understand how we need to change our weights and our bias factors such that we can make less errors that in the current iteration the model is making. So the average errors that the model is making, we are measuring it by the loss function. Now then the next step as part of this algorithm, it is to obtain specific amount of change in the loss function when we are making a small change in the weights parameters and in the bias parameters. And this is what we are also referring as gradients. The entire process of computing those gradients is called backpropagation. So backpropagation is basically a fancy way of referring to the process of calculating the first order partial derivative of the loss function with respect to each of our model parameters, including various weight parameters and the bias parameters. So this backpropagation is fundamental because it helps the algorithm to understand how much a change in loss function we will observe if we change each of those different weight parameters. Because this is the way that we need to supply this information to the optimization algorithm such as GAdam in order for the optimization algorithm to be able to update the model parameters. So basically, the output of the backprop is the input for the optimization algorithms such as GD, SGD, Adam, etc. So if we look at the specific example that we have looked into as part of the previous questions, we saw this very simple neural network where we had a small amount of hidden layers and small amount of hidden units, and we had just a couple of input signals. So as part of the forward pass, we then performed all the transformations, we have activated the neurons, and then we end up with this y-hat, which is the prediction of the response variable. So once we have the y-hat, then we also have cached our final values for our z-scores. So the z-scores were equal to the x multiplied by the weight parameters plus the bias parameters. So once we have this, then we can apply various differentiation rules specifically the change rule, but also we can make use of the differentiation rule of the summations and the one applied to the constants in order to update the gradients of the loss function with respect to the activation, so the dA, and then we can use this in order to obtain the gradients of the loss function with respect to the z, and then we can make use of this dA and then dz to obtain the gradients of the loss function with respect to the weight, so that is dv, and then finally in the similar way we can make use of dA and dz in order to obtain the gradients of the loss function with respect to the b's, so our bias vectors. What is important here is to keep in mind, without going too much into details of mathematical derivations, that in order to update the model parameters, we need to know the gradients of the loss function with respect to the weight parameter, so dv, as well as the gradients of the bias vectors, which is the first order partial derivative of the loss function with respect to the b's, so the bias vectors. But then in order to compute the dv and the db mathematically, we also need to first compute the gradients of the activations and the gradients of the z-scores. And the reason for that is because the weight factors and the bias vectors, they are part of the z-scores. So we have this chain of transformations we applied, which means that when we are performing differentiation, we then also need to perform this chain of differentiations in order to be able to obtain the gradients of the weights and gradients of the bias vectors in the first place. Which means that first we need to unpack what is the gradients of the activations, then we need to understand what is the gradients of the z-scores. We need to then use this, applying the chain rule in order to obtain this dv. As you can see here, z is equal to w multiplied with the activations a plus b, to be more specific, the transpose of the weight matrix multiplied with the activations matrix. Then we are adding the bias vectors, which forms our z's, and then to compute the gradients of the loss function with respect to the weight, so dv, we first need to take the partial derivative of the loss function j with respect to the z-scores, and then we need to multiply with the partial derivative of the z-scores with respect to the weight matrix in order to be able to compute this partial derivative dv. And then this is simply equal to the dz multiplied by the transpose of the activations matrix. And something similar we are also performing for obtaining the gradients of the bias vectors. I will not go too much into detail of the mathematical derivations. I will not go too much into details of the mathematical derivations of these gradients, because you will need to dive deep into these various partial derivatives. We need to also refresh our memory when it comes to using chain rules, the differentiation rules when it comes to sum of the values, when it comes to constant multiplied with the target value. And those are things that I would definitely recommend you to refresh when you are going through deep learning topics. But just to say, in the scope of the interview question, I just wanted to share this just to refresh your memory that in every time when we are trying to optimize the algorithm, in every step we are performing backpropagation, which includes calculating all these various gradients. And in order to compute the gradient with respect to the weights and the gradient with respect to the bias vectors, we first also need to calculate the gradients with respect to activations and the gradients with respect to the z-scores in order to then use them to calculate the gradients of the weights and the gradients of the bias vectors. And then to finalize this, the backpropagation is simply this process of computing the partial derivative of the loss function with respect to the weights and with respect to the bias vectors in order to supply them this as an input for our optimization algorithm, which is actually our next question. The next question is, how is backpropagation different from gradient descent? So during your deep learning interviews, you might get a question regarding the difference between backpropagation and gradient descent. This is usually a tricky one to confuse you, because sometimes it's very intuitive to describe the training process and to say that We first perform our forward pass. We then compute our loss function to see how well the model is training and the amount of error that it is making on average. And then we compute the gradients to understand how much of a change we have in the loss function when we apply the change in various parameters. And then we use this in order to supply it to the backward pass to continuously then update the model parameters up until the earlier layers in order to end up with a model that is performing better by coming from the deeper layers to the earlier layers. So this sounds very intuitive, and you might be still be asked a question, but how is this then different from the gradient descent? What is this difference specifically when it comes to backpropagation and GD? Well, the answer to this question actually is a very simple one, and this is just, in my opinion, a question to trick the interviewee. But I would just say that the backpropagation is the actual process of computing the gradients to understand how much a change in the loss function is there when we are changing the model parameters. And then the output of the backpropagation is simply used as an input for the gradient descent or any other optimization algorithm in order to update the model parameters. So the gradient descent is simply using the output of the backpropagation as an input because it's taking the computed gradients from the backprop as an input in order to then update the model parameters. So the backpropagation happens in the middle once we end up with our forward pass, and then the backpropagation is done, and then we are performing our backward pass. So we are using the backprop, and then we are continuously iteratively updating our model parameters from deeper layers to the earlier layers. And then this is what is done by the optimization algorithm. The next question is describe what vanishing gradient problem is and its impact on neural networks. So vanishing gradients happens when the gradients of a network, so loss functions with respect to the model parameters such as weights and the bias parameters, they become very small. And in some cases, they become entirely close to zero, which means they start to vanish as they propagate back through very deep layers to the earlier layers. And the result of this vanishing gradients is that the network is no longer able to learn dependencies in the data effectively, and the model is no longer able to update the model effectively, which means that the algorithm will end up not being optimized, and we will end up with a model that is unable and was not able to learn the actual dependencies in the data. Of course, that's something that we want to avoid, and we want to have a proper amount of gradients that we will use as part of the optimization algorithms like GD in order to obtain the model parameters, and then do this iteratively and continuously such that we will end up minimizing our loss function, and our model will be at a state that it will provide highly accurate predictions. So how do we get this vanishing gradient problem, and what is the reason of that? So as part of training of a neural network, we saw that in each training iteration, as part of the gradient descent algorithm, for instance, we would be using the entire training data to train our network and then perform these different transformations from very earlier layers to up until the last output layer to take the activations and then multiplying it with the weight matrix and then adding the bias parameters, compute the z-scores in this way, and then apply the activation function in order to activate those neurons. And then after this is done, in that specific hidden layer, the network is able to learn those different dependencies in the data and then learn the structure and then move on to the next layer and then to the next layer up until reaching the output layer. And then when we have our output layer, we then are able to calculate our predictions, so y hat, and then we are able to compare the y hat to the true labels or true values, and then understand what is this loss function, what is the average error that the model is making with this set of parameters. And then we are performing the backpropagation to compute gradients, then supplying it to the optimization algorithm in order to update the model parameters. And the way the optimization algorithm is doing it is opposite of the forward pass. So it is computing and taking the gradients, computing the corresponding updates, and then updating the weights and the bias vectors from deep layers to the earlier layers. And the problem with this is that we are performing all these transformations and then we are cumulatively every time multiplying those values. What this means is that in some cases, especially when we have deep network, when we have many hidden layers, by the time the network approaches from deep layers, the middle layers, and then earlier layers, after this multiplication of many of these weights and these gradients start to become very close to zero. When the gradients become very close to zero, it means that we have nothing then to update our weights and update our bias parameters. When we can no longer update our weights in our model, it means that the network is no longer able to properly learn, especially from the earlier layers when the gradient is vanishing. And this is then the problem because we want our model to continuously learn and continuously update those weights such that we will end up with the best set of parameters for the weights and the bias factors in order to minimize the loss function and then provide highly accurate predictions. Therefore, ideally, we want to ensure that those gradients do not vanish, so we combat the vanishing gradient problem, and our network is able to properly learn and understand these dependencies in our data, independent whether it's in the deep layers or in the earlier layers. So when it comes to description of this problem, try to focus on the weights because that's the biggest challenge when the gradients of the weights start to vanish, especially for earlier layers in a deep neural network. And that's something we want to avoid because then the model, in case of vanishing gradients problem, is not able to effectively learn. Another important thing that you can mention as part of your answer is that there are certain architectures that inherently are subject to this problem. And those are especially the RNNs, so recurrent neural networks, as well as LSTMs, GRUs, which are all inherently deep in their nature. Because unlike the original neural networks, like artificial neural networks that have a single input layer, they provide the input and then the neurons are being activated and they provide a single output. And the hidden layers, they are not interconnected. So they are not like the RNNs that take the input and then for each input, they provide the corresponding output. And then this hidden layer and the hidden unit is then being used as part of the next step and the next step. So they are not sequential based like RNNs. Then they are less likely to be prone to this vanishing gradient problem than the RNNs or because RNNs, TMs, and other sequence type of neural networks, they are inherently deep, which means that they have this multiple layers based on the amount of time steps that they have, which then makes these algorithms more prone to the vanishing gradient problem. The next question is, what is the connection between various activation functions and the vanishing gradient problem? So vanishing gradient problem is highly related to the choice of activation functions because there are certain activation functions that automatically result in vanishing gradient problem because of their inherent characteristics. And there are also activation functions which are known to not cause the vanishing gradient problem. And of course, we want to be aware of such activation functions and then not use them whenever we are aware that there can be a vanishing gradient problem. So here I tend to make a distinction between the sigmoid activation function and the tank activation function versus the ReLU, so rectifier linear unit, and the leaky ReLU activation functions. And the reason for that is because of their inherent property, what we are calling saturation. What this means is that in case of sigmoid activation function, for instance, when the activation is fz is equal to 1 divided to 1 plus e to the power minus z, it means that whenever the z or the z-scores is a very large negative number, let's say minus 1000, then the corresponding activation, the fz, will then be very close to 0, as you can see here, which is considered as a minimum for this sigmoid function. And then when the Z, so the Z score in this case from this graph, the X will be very large positive number, so it will be around 1000, then the corresponding function, the activation, will be around 1, so very close to 1. And as you can see, at some point after a certain level of X, for the positive values, independent how large this X will be, the corresponding activation will be very close to 1. And at some point, there will not even be a change in this area. This is exactly what we are referring as saturation, which means that when we have a very large negative or very large positive number, then there will no longer be any change in the corresponding activation. We will just end up approaching the maximum or the minimum of this function. In this case, for very large positive x's, the y will be around 1, and for very large negative numbers, the corresponding activation will be around 0. Therefore, in case of sigmoid activation function, we are saying that the sigmoid activation function suffers from saturation, and it is prone to causing the vanishing gradient problem. So it causes the gradients to vanish, especially when we have this very large values as a z-score. So it can be large positive or large negative. And actually the same holds for the tang activation function, because like you can see here, tang activation function, like sigmoid activation function, is this S-shaped activation function. And like sigmoid function, the tang also suffers from saturation. And in here, you can see that when we have x, which is very large positive number, let's say 1000, then the corresponding activation will be around 1. The same will hold if we change this x and we make it 2000 or 3000. So independent how much we will increase this large number for x, the corresponding activation will be the same. It will be close to 1, which is the maximum of this function. And then the same holds for the very large negative numbers for this activation function. So let's say the x is around minus 1000, then the corresponding activation will be around minus 1. But the same holds also when the x will be around minus 2000 or minus 10k. So this means that in case of tang activation function, as in case of sigmoid activation function, when we have very large positive or very large negative values and we want to see how much we can activate them using this activation function, then the corresponding activation value is around the extreme of this function. So minus 1 and 1 in case of tang function, and the 0 and 1 in case of sigmoid activation function. So therefore, like in case of sigmoid activation function, we are saying that tang activation function suffers from saturation, and this means that tang activation function inherently causes the vanishing gradient problem because it's causing the gradients to vanish, and that's something that we want to avoid. So one thing that we can keep in mind is that the sigmoid activation function and tang activation functions are great when it comes to the output layer because they have this nice properties in transforming the values between certain ranges. Like in case of sigmoid function, it transforms the values, any values between 0 and 1, which is great when we want to have an output in the form of probabilities, great for classification type of problems. But when it comes to using these activation functions for hidden layers, that's something that we want to avoid. So my suggestion would be to use sigmoid activation function or hyperbolic tang activation function for your output layers, but then do not use it for your hidden layers because they are prone to vanishing gradient problem. The next set of activation functions that we will discuss today are the rectifier linear unit and the leaky ReLU, so leaky rectifier linear unit. Unlike the sigmoid activation function and the tang activation function, ReLU or leaky ReLU, they both do not suffer from saturation. This means that they are then no longer causing the vanishing gradient problem, and they are great for using it as part of the hidden layers. You can see that for the cases when we take very large positive x, then the corresponding activations will change. And when we go from, let's say, 1000 to 2000, from 2000 till 10k, we will have the corresponding activation values also change a lot, which means that the activation function will not result in the gradients coming very close to 0. which is what we are describing as a vanishing gradients. So as part of this, ReLU will not be causing the vanishing gradient problem, which is something that is great, especially when we are using them as part of our hidden layers. The same also holds for the leaky ReLU, which you can see here, because the two are very similar to each other, and with only difference that leaky ReLU does consider activating, at some extent, the negative neurons, which means that when x is negative value, so from minus infinity till 0, you can see that the corresponding activations are not 0, but they are equal to 0.01. So this means that unlike the sigmoid and tank activation function, those two are not suffering from saturation, so their activation values will change and will not be close to the same extreme of the function when we provide as an input very large positive or very large negative values, which means that they are ideal for using as part of the hidden layers, such that the network can continuously effectively learn those hidden dependencies in the data. Therefore, we are saying use ReLU and leaky ReLU as part of your hidden layers to activate those neurons. And whenever you approach this output layer, for the output layer, use the sigmoid function or the tank activation function. The next question is, there is a neuron in the hidden layer that always results in a large error in backpropagation. And what could be the reason for that? So there can be many reasons that can result in this specific neuron or some of the neurons to consistently result in large error as part of the backpropagation in a neural network. So the first reason could be poor initialization of the weights. And what this means is that in the very beginning, when we are starting the training process, we need to initialize the weight parameters and the bias parameters such that the network can take these initial values and then perform the forward pass, compute the loss, and then use this as an input for the optimization algorithm like GD, SGD, in order to then update those weight parameters iteratively. But if we do this initialization of the weights not in a proper way, which means that we are not using the right distribution to randomly sample from it, or we are just providing a wrong or not proper value to this weight and the bias parameters, it means that this will, right from the beginning, skew off the learning process for those specific neurons. And if we, right from the beginning, perform the learning process in an improper way, and we are skewing those learning processes in every iteration, this means that the next iteration that will be based in the first iteration that started wrongly from the first pass, it will also be done in the wrong way. And then the next time and the next time, this process will continue to result every time in an improper learning and in the large error as part of the calculation of the loss and then backpropagation. And another reason for this can be the vanishing or the exploding gradients. So if the gradients become very small and the weights of the neurons, especially in deep network, no longer start to update those different parameters, this means that we can persistently make those large errors in specific neurons because we are no longer able to effectively learn those dependencies in the model, and that specific neuron will not be correctly activated and the corresponding weights will not be updated in order to improve the accuracy of the predictions for those specific neurons. And of course, the same holds for the opposite problem, which is the exploding gradient problem. If we are making too much of an update and the neurons are not being properly activated, the corresponding weights are not being properly updated, this means that we will be consistently making those large errors for those neurons. Another reason for this can be inadequate learning rate, which means that if we have too high learning rate or too small learning rate, we might be overshooting the optimal values during the training or undershooting, so insufficiently updating those weight parameters and those bias parameters. And this means that we will then continuously make large errors for those specific neurons. Therefore, it's really important to optimize these hyperparameters in our model such that the model can make consistent updates and consistently improve the model parameters, which means also improve the learning process. Another reason can be improper activation function, because activation functions can significantly impact the learning process. The way we activate our neurons will be a defining factor for the neural network to properly learn those dependencies in the data and then understand how the weight parameters and the parameters need to be updated such that the learning will be optimized. The next question is, what do you understand by a computational graph? So computational graph is a way to visualize complex operations that we are using as part of training models, as part of various type of optimization processes. And it's a great way to showcase all the steps that we are taking when going from very simple variables or objects till applying various transformations and then getting to the very complex functions. So one way that we are using computational graphs are when we are visualizing the neural networks. So we saw this very basic representation and a basic neural network in the earlier interview questions. And this one is a vivid example of applying computational graph. In here, you can see that we are using the nodes and the edges in order to describe the computational graph. And in the computational graph, we usually have the nodes representing objects or variables, and then the edges usually represent the type of operations or transformations that we are applying to those objects or variables. In this case, you can see that we have input signals x1, x2, x3, which are simply the variables. Those are the nodes at the initial layer. And then we are showcasing that we are applying those edges, these arrows that go onto our first hidden layer. In this hidden layer, you can see that we have the z-scores per hidden unit, and then we have the corresponding activation. So z1, a1, corresponding to the first hidden layer's first hidden unit. And then we have the z2, a2, and then z3, a3, z4, a4, because we have 4 different hidden units as part of our single hidden layer. And then we apply another transformation when we go from the first hidden layer to the output layer. What you can see here is that we have these arrows that showcase how we go from x1, x2, x3, so our input data, to the z-scores, and then we apply the activation on the z-scores to compute our activation scores, and then we use these activation scores from the final layer in order to go on to our predictions, which is the y-hat. You can see here that we are using this final output layer to compute the y-hat. And this is something that we are doing to visualize this process of computing first the z-scores based on the xi, the input data, multiplied with the transpose of the weight matrix w plus b. So this is at the observation layer, observation level. And then the yi hat is then simply equal to ai equal to sigma zi. And what we are doing here is that we are computing the z-scores, and then after z-scores, we are applying this sigma function, which is the activation function that we are getting. And then after the activation function is applied on the z-scores, we are then computing and getting the activation scores, and then using this activation scores to compute our yi hat. And then once we have our yi hat, which is our prediction, then we are comparing it to the true values, so the yi, and then we are computing our loss, so the amount of error that the model is making. So you can see what are those steps that we are making, and when we have more hidden layers, not just one, but let's say 3, 4, or billions of those layers, then we will end up having a very hard time understanding those different steps, let alone to visualize it or to showcase how many layers we have. And each time using different indices, each time performing the same transformations from input data to z-scores and then to activation function. From after activation function, we get the activation scores. You get the idea. So it's then much easier to showcase all these calculations using this computational graph. So basically, instead of using all these transformations, these matrices that can be hard to understand, we are using the computational graph to simplify the process and to visualize it, to showcase how we go from the input variables, and then we apply all these transformations, and then we end up with the predictions. And then this computational graph can be made a bit more difficult by also showcasing the other side of the story. So getting the predictions and then applying backpropagation, and then from backpropagation to the actual gradient calculations, and then the updates of the parameters. But then just for simplicity, I thought I will just use this simple neural network to showcase this. But of course, the idea behind computational graph is not just to showcase a forward pass, but also to showcase the entire network, including the backpropagation, so calculation of the gradient. What is gradient clipping and their impact on neural network? So we just saw the residual connections, and we saw that residual connections, especially for deep neural network, and specifically for the cases like RNNs, LSTMs, when we have the sequential nature with too many layers, we can have this vanishing gradient problem, and residual connections can help you solve this problem. Now, gradient clipping is solving the opposite problem. So it's solving the exploding gradient problem. Whenever we have certain deep neural networks like RNNs, LSTMs, because we are each time using these transformations and we are using a cumulative nature and multiplying all these weights towards each other through this process, and we are using the previous hidden state to update the new hidden state, so the next hidden state and the next one, it also means that when we are going through these layers, during the optimization process, after backprop is done, we need to perform all these transformations. And by the time we come through the earlier layers, it can be that we have exploding gradients. So the gradients become so large that it starts to impact the entire performance of the model. We are starting to make too big over jumps, and the updates that we are starting to get and optimization process is starting to make too much of these oscillations towards different directions. So we are seeing this erratic behavior as part of our optimization process. And that's definitely not something that we want to have, because exploding gradients means that we have unstable neural network, and this also means that the update of the weights will be too large, and this will then result in not well performing and not properly trained neural network. Now, to avoid all these problems, the way we can solve this exploding gradient problem is by using the gradient clipping. What gradient clipping does is that it basically clips the gradients at a certain level. So there is a threshold, which is the parameter that we are using for gradient clipping. And whenever the gradient becomes too large, so higher than the threshold, then we will be clipping that gradient to ensure that this gradient is not too large and we are not updating our weight parameters or bias factors too much. So in this way, what we are doing is that we are kind of stabilizing our neural network, which is especially important for architectures like LSTMs, RNNs, GRUs, which have this sequential nature of the data with too many layers. And in this way, we will ensure that we do not have these erratic jumps in our neural network optimization process, and we will end up with a stable network that is able to properly learn the interdependencies. The next question is, what is cross entropy and why it is preferred as a cost function for multi-class classification type of problems? So cross entropy, which is also known as log loss, it measures the performance of a classification model that has an output in the terms of probabilities, which are values between 0 and 1. So whenever you are dealing with classification type of problem, let's say you want to classify whether an image is of a cat or a dog, or the house can be classified as an old house versus a new house. In all those cases, when you have these labels and you want the model to provide a probability to each of those classes per observation, such that you will have as an output of your model that the house A has 50% probability of being classified as new, 50% probability of being classified as old, or the cat has 70% probability of being a cat image, or this image has 30% probability of being a dog image. In all those cases, when you are dealing with this type of problems, you can apply the cross entropy as a loss function. And the cross entropy is measured as this negative of the sum of the y log p plus 1 minus y and then log 1 minus p, where y is the actual label. So in binary classification, this can be, for instance, 1 and 0, and then p is the predicted probability. So in this case, the p will be then the value between 0 and 1, and then the y is the corresponding label. So let's say a label 0 when you are dealing with a cat image and label 1 when you are dealing with a dog image. And the mathematical explanation behind this formula is out of the scope of this question, so I will not be going into that details. But if you are interested in that, make sure to check out the logistic regression model. This is part of my Machine Learning Fundamentals Handbook, which you can check out. And this one includes also logistic regression, which explains step by step how we end up with this log likelihood function and how then we go from the products to summations after applying the logarithmic function, so we get the log odds, and then we multiply it with the minus because this is the negative of the likelihood function, given that we want to ideally minimize the loss function, and this is the opposite of the likelihood function. And in this case, what this showcases is that we will end up getting a value that tells how well the model is performing in terms of classification. So the cross entropy then will tell us whether the model is doing a good job in terms of classifying the observation to a certain class. The next question is, what kind of loss function we can apply when we are dealing with multi-class classification? So in this case, when dealing with multi-class classification, we can use the multi-class cross entropy, which is often referred as a softmax function. So softmax loss function is a great way to measure the performance of a model that wants to classify observations to one of the multiple classes, which means that we are no longer dealing with binary classification, but we are dealing with multi-class classification. So one example of such case is when we want to classify an image to be from summer theme, to be from spring theme, or from winter theme. Given that we have 3 different possible classes, we are no longer dealing with binary classification, but we are dealing with multi-class classification, which means that we also need to have a proper way to measure the performance of the model that will do this classification. And softmax is doing exactly this. So instead of getting the pair observation 2 different values, which will say what is the probability of that observation belonging to class 1 or class 2, instead we will have a larger vector pair observation, depending on the number of classes you will be having. In this specific example, we will end up having 3 different values, so one vector with 3 different entries, pair observation, saying what is the probability that this picture is from winter scene, what is the probability of this observation coming from summer theme, and the third one, what is the probability that the observation comes from a spring theme. In this way, we will then have all the classes with the corresponding probabilities. So as in case of the cross entropy, also in case of the softmax, When we have a small value for the softmax, it means that the model is performing a good job in terms of classifying observations to different classes, and we have well-separated classes. And one thing to keep in mind when we are comparing cross entropy and multi-class cross entropy or the softmax is that we are usually using this whenever we have more than two classes. And you might recall from the transformer model introduction from the paper Attention is All You Need that as part of this architecture of transformers, a softmax layer is also applied as part of the multi-class classification. So when we are computing our activation scores, and also at the end, when we want to transform our output to values that make sense and to measure the performance of the transformer. The next question is, what is SGD and why it is used in training neural networks? So SGD is, like GD, an optimization algorithm that is used in deep learning in order to optimize the performance of a deep learning model and to find a set of model parameters that will minimize the loss function by iteratively improving the parameters of the model, including the weight parameters and the bias parameters. So the SGD, the way it performs the updates of model parameters is by using a randomly selected single or just few training observations. So unlike the GD, which was using the entire training data to update the model parameters in one iteration, in case of SGD, the SGD is using just single randomly selected training observation to perform the update. So what this basically means is that instead of using the entire training data for each update, SGD is making those updates in the model parameters per training observation. And there is also an importance of this random component, so the stochastic element in this algorithm, hence also the name stochastic gradient descent. Because SGD is randomly sampling from training observations a single or just couple of training data points, and then using that it performs the forward pass, so it computes the Z scores and then computes the activation scores after applying the activation function, then reaches the end of the forward pass and the network computes the output, so the y hat, and then computes the loss, and then we perform the backprop only on those few data points. And then we are getting the gradients, which are then no longer the exact gradients. So in SGD, given that we are using only a randomly selected few data points or a single data point, instead of having the actual gradients, we are estimating those true gradients because the true gradients are based on the entire training data. And in SGD, for this optimization, we are using only few data points. What this means is that we are getting an imperfect estimate of those gradients as part of the backpropagation, which means that the gradients will contain this noise. And the result of this is that we are making the optimization process much more efficient because we are making those parameter updates very quickly based on pass by using only a few data points. And training a neural network on just a few data points is much faster and easier than using an entire training data for a single update. But this comes at the cost of the quality of the SGD, because when we are using only a few data points to train the model and then compute gradients, which are the estimate of the true gradients, then these gradients will be very noisy. They will be imperfect and most likely far off from the actual gradients, which also means that we will make a less accurate updates to our model parameters. And this means that every time when the optimization algorithm is trying to find that global optimum and make those movements per iteration to move one step closer towards that optimum, most of the time it will end up making wrong decisions and will pick the wrong direction, given that the gradient is the source of that choice of what direction it needs to take. And every time it will make those oscillations, those movements, which will be very erratic And it will end up most of the time discovering the local optimum instead of the global optimum. Because every time when it's using just a very small part of the training data, it's estimating the gradients, which are noisy, which means that the direction it will take will most likely be also a wrong one. And when you make those wrong directions and wrong moves every time, you will start to oscillate. And this is exactly what HGD is doing. It's making those wrong decision choice when it comes to direction of the optimization, and it will end up discovering a local optimum instead of the global one. And therefore, the HGD is also known to be a bad optimizer. It is efficient, it is great in terms of convergence time, in terms of the memory usage, because storing a model and that is based on a very small data and storing that small data into the memory is not computationally heavy and memory heavy, but this comes at the cost of this quality of the optimizer. And in the upcoming interview questions, we will learn how we can adjust this HGD algorithm in order to improve the quality of this optimization technique. The next question is, why does stochastic gradient descent, or the SGD, oscillate towards local minimum? So there are a few reasons why this oscillation happens. But first, let's discuss what oscillation is. So oscillation is the movement that we have when we're trying to find the global optimum. So whenever we are trying to optimize the algorithm by using an optimization method like GD, SGD, RMSProp, AdamW, we are trying to minimize the loss function. And ideally, we want to change iteratively our model parameters so much that we will end up with the set of parameters resulting in the minimum, so global minimum of the loss function. Not just local minimum, but the global one. And the difference between the two is that the local minimum might appear as if it's the minimum of the loss function, but it holds only for a certain area when we are looking at this optimization process. Whereas the global optimum is really the mean, as the real minimum of the loss function. And that's exactly that we are trying to chase. When we have too much oscillations, which means too much movements, when we are trying to find the direction towards that global optimum, then this might become problematic because we then are making too many movements every time. And if we are making those movements that are opposite or they are towards the wrong direction, then this will end up resulting in discovering local optimum instead of global optimum, something that we are trying to avoid. And the oscillations happen much more often in the SGD compared to GD, because in case of GD, we are using the entire training data in order to compute the gradient, so the partial derivative of the loss function with respect to the parameters of the model. Whereas in case of SGD, we learned that we are using just randomly sampled single or few training data points in order to update the gradients and to use these gradients to update the model parameters. This then, for SGD, results in having too many of these oscillations because the random subsets that we are using, they are much smaller than training data. They do not contain all the information in training data. And this means that the gradients that we are calculating in each step, when we are using entirely different and very small data, can differ significantly. One time we can have one direction, the other time an entirely different direction for our movement in our optimization process. And this huge difference, this variability in the direction, because of the huge difference in the gradients, can result in too often of these oscillations, so too many of bouncing around towards the area to find the right direction towards the global optimum, in this case, the minimum of the loss function. So that's the first reason, the random subsets. The second reason why in SGD we have too many of those oscillations, those movements, is the step size. So step size, the learning rate can define how much we need to update the weights or the bias parameters. And the magnitude of this updates is determined by this learning rate, which then also plays a role how different these movements will be and how large the jumps will be when we are looking at the oscillations. So the third reason why the SGD will suffer from too many of oscillations, which is a bad thing, because it will result in finding a local optimum instead of the global optimum too many times, is the imperfect estimates. So when we are computing the gradients of the loss function with respect to the weight parameters or the bias factors, then if this is done on a small sample of the training data, then the gradients will be noisy. Whereas if we were to use the entire training data that contains all the information about the relationships between the features and just in general in the data, then the gradients will be much less noisy. They will be much more accurate. Therefore, because we are using the gradients based on small data as estimate of the actual gradients, which is based on the entire training data, this introduces a noise, so imperfection when it comes to estimating this true gradient. And this imperfection can result in updates that do not always point directly towards the global optimum. And this will then cause these oscillations in the SGD. So at high level, I would say that there are three reasons why SGD will have too many of these oscillations. The first one is the random subsets, the second one is the step size, and the third one is definitely the imperfect estimates of the gradients. The next question is, how is GD different from SGD? So what is the difference between the gradient descent and the stochastic gradient descent? So by now, given that we have gone too much into details of SGD, I will just give you a high-level summary of the differences of the two. So for this question, I would answer by making use of 4 different factors that cause a difference between the GD and SGD. So the first factor is the data usage. The second one is the update frequency. The third one is the computational efficiency. And the fourth one is the convergence pattern. So let's go into each of these factors one by one. So gradient descent uses the entire training data when training the model and computing the gradients and using this gradient as part of backpropagation process to update the model parameters. However, SGD, unlike GD, is not using the entire training data when performing the training process and updating the model parameters in one go. Instead, what SGD does is that it uses just a randomly sampled single or just 2 training data points when performing the training and when using the gradients based on the 2 points in order to update the model parameters. So that's the data usage and the amount of data that SGD is using versus the GD. So the second difference is the update frequency. So given that GD updates the model parameters based on the entire training data every time, it makes much less of these updates compared to the SGD. Because SGD then very frequently, every time for this single data point or just 2 training data points, it updates the model parameters. Unlike the GD that has to use the entire training data for just one single set of update. So this causes then SGD to make those updates much more frequently when using just a very small data. So that's about the difference in terms of update frequency. Then another difference is the computational efficiency. So GD is less computationally efficient than SGD because GD has to use this entire training data, make the computations of backpropagation, and then update the model parameters based on this entire training data, which can be computationally heavy, especially if you are dealing with very large data and very complex data. And unlike GD, SGD is much more efficient and very fast because it's using a very small amount of data to perform the updates, which means that it requires less amount of memory to store the data. It uses small data, and it will then take much less amount of time to find a global optimum, or at least it thinks that it finds the global optimum. So the convergence is much faster in case of SGD compared to GD, which makes it much more efficient than the GD. Then the final factor that I would mention as part of this question is the convergence pattern. So GD is known to be smoother and of higher quality as an optimization algorithm than SGD. HGD is known to be a bad optimizer. And the reason for this is because that the efficiency of HGD comes at a cost of the quality of it, of finding the global optimum. So HGD makes all these oscillations, given that it's using a very small part of the training data when estimating the true gradients. And unlike HGD, GD is using the entire training data, so it doesn't need to estimate the gradients. It's able to determine the exact gradients. And this causes a lot of oscillations in case of HGD. And in case of GD, we don't need to make all these oscillations. So the amount of movements that the algorithm is making is much smaller. And that's why it takes much less amount of time for HGD to find the global optimum. But unfortunately, most of the time, it confuses the global optimum with the local optimum. So HGD ends up making this many movements, and it ends up discovering the local optimum and confuses it with the global optimum, which is of course not desirable, because we would like to have the actual global optimum, so the set of parameters that will actually minimize and find the minimum value of the loss function. And HGD is the opposite because it's using the true gradients, and it is most of the time able to identify the true global optimum. So the next question is, how can we use optimization methods like GD, but in a more improved way? So how we can improve the GD, and what is the role of the momentum term? So whenever you hear momentum and then GD, try to automatically focus on the HGD with momentum, because HGD with momentum is basically the improved version of HGD. And as far as you know the difference between HGD and GD, it will be much easier for you to explain what is the HGD with momentum. So we just discussed that the GD suffers from oscillation, so too many of those movements. And a lot of time, because we are using a small amount of training data to estimate the true gradients, this will result in having entirely different gradients and too much of this different sorts of updates in the weights. And of course, that's something that we want to avoid, because we saw and we explained that too many of those movements will end up causing the optimization algorithm to mistakenly confuse the global optimum and the local optimum. So it will pick the local optimum, think that it's a global optimum, but it's not the case. So to solve this problem and to improve the HGD algorithm, while taking into account that HGD in many aspects is much better than the GD, we came up with this HGD with momentum algorithm, where HGD with momentum will take basically the benefits of the HGD, and then it will also try to address the biggest disadvantage of HGD, which is this too many of these oscillations. And the way HGD with momentum does is that it uses this momentum and it introduces this idea of momentum. So momentum is basically a way to find and put the optimization algorithm towards better direction and reduce the amount of oscillations. So the amount of these random movements. And the way that it does is that it tries to add a fraction of this previous updates that we made on the model parameters, which then we assume will be a good indication of the more accurate direction in this specific time step. So imagine that we are at time step t and we need to make the update. Then what momentum does is that it looks at all the previous updates and uses the more recent updates more heavily and says that the more recent updates most likely will be better representation of the direction that we need to take versus the very old updates. And these updates in the optimization process, these very recent ones, when we take them into account, then we can have a better way of and more accurate way of updating the model parameters. So let's look into mathematical representation just for a quick refreshment. So what the HGD with momentum tries to do is to accelerate this conversion process. And instead of having too many of the movements towards the different direction and having too different often gradients and updates, it tries to stabilize this process and have more constant updates. And in here, you can see that as part of the momentum, we are obtaining this momentum term, which is equal to Vt plus 1 for the update at the time step of t plus 1. What it does is that it takes this gamma multiplies it by Vt plus the learning rate, eta, and then the gradient, where you can see that this inflated triangle and then underneath the theta and then j theta t simply means the gradient of the loss function with respect to the parameter theta. And what it's basically doing is that it says we are computing this momentum term for the time step of t plus 1, which is based on the previous updates through this term gamma multiplied by Vt, plus the common term that we saw before for the SGD, and for GD, which is basically using this eta learning rate multiplied by the first order partial derivative of the loss function with respect to the parameter theta. So we then are using this momentum term to simply subtract it from our current parameter theta t in order to obtain the new version, so the updated version, which is theta t plus 1, where theta is simply the model parameter. So in this way, what we are doing is that we are performing the updates in more consistent way. So we are introducing consistency into the direction by weighting the recent adjustments more heavily, and this builds up the momentum, hence the name momentum. So the momentum builds up this speed towards the direction of the global optimum in more consistent gradients, enhancing the movement towards this global optimum, so the global minimum of the loss function. And this then on its turn will improve, of course, the quality of the optimization algorithm, and we will end up discovering the global optimum rather than local optimum. So to summarize what this SGD with momentum does is that it basically takes the SGD algorithm. So it again uses a small training data when performing the model parameter updates. But unlike the SGD, what SGD with momentum does is that it tries to replicate the GD's quality when it comes to the finding the actual global optimum. And the way it does that is by introducing this momentum term, which helps also to introduce consistency in the updates and to reduce the oscillations the algorithm is making by having much more smoother path towards discovering the actual global optimum of the loss function. The next question is compare batch gradient descent to mini-batch gradient descent and to stochastic gradient descent. So here we have three different versions of the gradient descent algorithm. The traditional batch gradient descent, often referred as GD simply. The second algorithm is the mini-batch gradient descent, and the third algorithm is the SGD, or the stochastic gradient descent. So the three algorithms are very close to each other. They do differ in terms of their efficiency and the amount of data that they are using when performing each of this model training and the model parameters update. So let's go through them one by one. So the batch gradient descent, this is the original GD. This method involves the traditional approach of using the entire training data for each iteration when computing the gradient, so doing the backprop, and then taking these gradients as an input for the optimization algorithm to perform a single update for these model parameters. Then on to the next iteration when again using the entire training data to compute the gradients and to update the model parameters. So here for the batch gradient descent, we are not estimating the true gradients, but we are actually computing the gradients because we have the entire training data. Now, batch gradient descent, thanks to this quality of using the entire training data, has a very high quality. So it's very stable, it's able to identify the actual global optimum. However, this comes at a cost of efficiency because the batch gradient descent uses the entire training data. It needs to every time put this entire training data into the memory, and it is very slow when it comes to performing the optimization, especially when dealing with large and complex data sets. Now, next we have the other extreme of the batch gradient descent, which is SGD. So SGD, unlike the GD, and we saw this previously when discussing the previous interview questions, that SGD is using stochastically, so randomly sampled single or just few training observations in order to perform the training, so computing the gradients, performing the backprop, and then using optimization to update the model parameters in each iteration. Which means that we do not compute the actual gradients, but we actually are estimating the true gradients. because we are using just a small part of the training data. So this, of course, comes at the cost of the quality of the algorithm. Although it's efficient to use only small sample from the training data when doing the backprop, the training, you don't need to store the entire training data into the memory, but just a very small portion of it, and we perform the model updates quickly, but then we find the so-called optimum much quicker compared to the GD. But this comes at a cost of the quality of the algorithm, because then it starts to make too many of these oscillations due to these noisy gradients, which then ends up confusing the global optimum with the local optimum. And then finally, we have our third optimization algorithm, which is the mini-batch gradient descent. And this mini-batch gradient descent is basically the silver lining between the batch gradient descent and the original SGD, so stochastic gradient descent. And the way mini-batch works is that it tries to strike this balance between the traditional GD and the SGD. It tries to take the advantages of the SGD when it comes to the efficiency and combine it with the advantages of GD when it comes to stability and consistency of the updates and finding the actual global optimum. And the way that it does that is by randomly sampling the training observations in two batches, where the batch is much bigger compared to SGD, and it then uses this smaller portions of training data in each iteration to do the backprop and then to update the model parameters. So think of this like the k-fold cross-validation, when we are sampling our training data into this k different folds, in this case batches, and then we are using this in order to train the model, and then in case of neural networks, to use the mini batch gradient descent to update the model parameters such as weights and bias vectors. So the three have a lot of similarities, but they also have differences. And in this interview question, your interviewer is trying to test whether you understand the benefits of one and two, and what is the purpose of having mini batch gradient descent. So the next question is how to decide the batch size in a deep learning considering both too small and too large sizes. This question is a very important question where the interviewer is trying to test whether you understand what is the impact of the batch size on your entire algorithm, the quality of it. So here, your interviewer wants to know your understanding of the batch size impact on the gradient noise, on the bias of your model, on the variance of the model, on the generalization of the model, the convergence of the model, the efficiency, especially the memory usage. So we just discussed and compared the traditional batch gradient descent to the mini batch gradient descent and to the SGD. And here we have already touched on this idea of using very large training data, using a small part of the training data like mini batches, versus using even smaller, like a single or very few observations randomly sampled from training data. And this question is exactly related to that. So let's say we have this mini batch gradient descent, and we want to understand what is this batch size that we need to use. What are the amount of observations that we need to put in single batch when performing the training process, performing the backprop, and then updating the model parameters in each iteration. So let's compare the small batch size versus large batch size with respect to all these factors that I just mentioned. So when it comes to the small batch sizes, which means that let's say we have 2 up to 32 as the batch size, so we have 1 till 32 observations that are in our batch. So in this case, the gradient noise will be, of course, very high. And the reason for that is because we are using a very small part of the training data when estimating the gradients of our model, the true gradients. And this, of course, means that this estimate will most likely not be the proper estimate for the true gradient, because we are using just a very small part of the training data. And this then introduces a lot of noise into our model. Versus when we have a large batch size, then the gradient noise will be lower because we are using a larger training part training data part when performing the estimation of the true gradient. Then we have the convergence. So when it comes to the small batch sizes, the convergence tends to be, the quality of the convergence tends to be worse, because it's like the SGD, it tends to make all of these oscillations, and though the convergence will be speedy, so it will be quick, but it will most likely discover the local optimum versus the global optimum. While when we have large batch size, then the algorithm will often converge to sharper minimum, so the actual global optimum, and the process might take slower, but the quality will be higher. Then we have the generalization factor. Generalization basically refers to the idea of overfitting. How much the model is actually memorizing the training data versus being able to perform equally well on the unseen data. Now, whenever we are using the entire training data, which a lot of times will contain noise, then the model, by every time using this large portion or the entire training data when training the model, it will be more likely to use this noise in order to obtain the gradients and then perform model parameter updates. What this basically means is that for these large batch sizes, then the generalization will be potentially worse, because the model will be memorizing the training data. It will most likely catch this noise as normal points, and it will be much more focused on the training data. Whereas when we have a smaller batch size, then we are randomly selecting a much smaller portion of the training data, and the likelihood of having a noise in that small part of the training data in the small batch is lower, which means that the likelihood of the model following this noise and overfitting and performing very worse on the unseen new training data, new test data, is lower. So just to summarize, when it comes to generalization, because it's really important, when we have small batch size, then we have potentially better generalizing model, because we will then using a small portion of the training data, and the model will be less inclined to memorize the training data, and it will perform equally well on the new unseen data, versus the large batch size, which will intend and will have higher likelihood of following the noise in the data and then not generalizing well on the unseen data. Then we have the bias. So small batch size case, then the bias will be potentially lower, because the model will be less likely to overfit to the training pattern. Whenever we have a model overfitting, then the bias will be higher. If we have lower chance for overfitting, then the bias will be lower. This also means that generalization and the bias are very much related, as we also know in the traditional machine learning, and the opposite holds for the large batch size, because for the large batch size, we saw that it generalizes worse at a lesser extent, which also means that the bias will most likely be higher in case of large batch size. So when it comes to the variance, then in case of small batch size, the variance is higher, because we are every time using a different part of the training data and small part. So there will be much more of these oscillations and the exploration when it comes to finding the global optimum. Whereas in case of large batch size, then we have a variance which is much lower, because we are making less explorations to find the solution of the optimization process. Then we have the computational cost and the memory usage. For large batch sizes, when we have large amount of data, then we will be storing much more data into the memory. It also means that the convergence will be slower and the computational cost will be higher. And the smaller is the batch size, the lower is computational cost, and the lower is the memory usage. So the next question is, how does the batch size impact the performance of a deep learning model? So a batch size, which is a number of training samples that we use per iteration when performing the training of the model, computing the gradients as part of backprop, and then updating our model parameters per iteration, plays a significant role in the performance and the final outcome of the deep learning model. There are a few things that I would advise to mention as part of your interview answer to this question. And the first one is definitely the training time. And here it's important to analyze this with respect to the training time per iteration, training time per epoch, and the overall training time, because the three are actually very much different when we compare the batch size. And here we would like to compare the small batch versus the large batch. So when it comes to this smaller batch sizes, which means that we are using smaller portion of the training data per iteration to compute the gradients and to perform the updates, this means that per epoch, so it means when we want to pass the entire training data, which is one epoch, it means that we need to have many of these iterations, because per iteration we need to have, we just use a small portion of the training data, and the smaller is the batch size, it means the higher will be number of iterations per epoch to perform to ensure that the entire training data has been used for updating the model parameters. So this also means that the training time will be longer per epoch compared to the larger batch sizes where we will go through the entire training data. So per epoch, we will have less number of iterations. So it will take much less time per epoch to train the model. But the problem is that in case of larger batch sizes, it can be memory intensive and may not always even be feasible when we have a very small machine, not a powerful one, in order to perform the training. So it comes also with hardware limitations. Then another factor you can mention is the memory usage. So a larger batch size requires more memory, whereas a smaller batch size requires less memory. So this is another factor that comes into the overall performance of your model. And then we have the convergence quality. This we have spoken a lot about, so I will just briefly mention. When we have smaller batch size, the smaller is the batch size, the higher is usually the generalization of the model, but usually the lower is the convergence quality because it's more likely to catch the local optimum instead of global optimum. Then when it comes to the learning dynamics, then the batch size will impact the model's ability to escape the local optimum. If we have the smaller batch sizes and we are using them when to estimate the true gradient, then this gradient will be noisy, which also means that the learning will be inconsistent and it is more likely to impact the quality of the optimization process and to catch the local optimum instead of global optimum. And overall, if your batch size is small, then usually the algorithm is much more unstable, rather than when we have large batch size and the algorithm is much more consistent in the updates of model parameters. The next question is, what is Hessian and how it can be used for faster training? What are its disadvantages? So if you got a course in differential theory, then you most likely know what Hessian means. Here, I will just give you a very high-level summary of what Hessian is, and I will go in much more detail into the impact of using Hessian in deep learning. So Hessian comes from differential theory, and it is basically a matrix that contains the second-order partial derivative of a function with respect to the parameters. In case of deep learning, as part of the optimization process, Hessian can play a role of getting better and more accurate estimates of the gradients, because it then will compute the second order partial derivative of the loss function with respect to the model parameters. And the reason why we are using Hessian in some cases, in some adaptive learning optimization algorithms, which are more improved version of SGD or SGD with momentum, is to have a better estimate, less noisy estimates of the true gradients. And you might recall that when we were discussing the SGD and SGD with momentum, we were saying that our primary goal is to reduce the number of oscillations as much as possible. Because when we are using a small batch size or just few training observations to perform our backprop and obtain the estimate of the true gradients, then usually this ends up introducing instability in our model, because these gradients, this estimate of the gradients, are not proper estimates of the true gradients. And to improve this, when we use Hessians are known to be much more accurate estimate of the gradients, and they can help the algorithm, the optimization algorithm, to move towards more correct direction when we are trying to update the model parameters. So using the same amount of data, but having less noisy gradients and making more correct updates and take a smoother direction towards the global optimum. Now, this comes with certain disadvantages because it's not that easy to compute the Hessian. So if we look at this example, this is an example of an Hessian matrix, and you can see that on the diagonal we have simply the second order derivative of the function f with respect to the parameter x1. But then when it comes to multiple parameters, so when we have multiple parameters in our model, we then need to obtain the partial derivative of the function, in our case, the loss function, with respect to the model parameters. And when you do this computation manually, just as an example, just for fun, you will discover that in some cases, when you have many parameters in your model, then it will be sometimes super difficult to compute these second order partial derivatives. Beside of that, this comes also at the cost of the computational resources when it comes to using Hessian as part of your optimization algorithm, because this results in having this complicated functions putting into the memory and storing this information into the memory. And this Hessian matrix can be extremely large for deep neural network models. And this will then result in the high number of parameters, making it sometimes computationally infeasible or very expensive to calculate and to then invert the gradients. Then the other disadvantage of this Hessian usage is that we might have a risk of overfitting, because when we are using this second order derivative, the second order partial derivative, as a way to estimate the two gradients, we might be over-relying on this Hessian for training acceleration. And this might result in the model memorizing the training data and overly relying on the training data when performing the parameter updates, which will mean that the model will less likely generalize well on non-seen data, which is of course a problem, because then our model is overfitting and it will be able to generalize well on an unseen data, which is our end goal. The next question is discuss the concept of an adaptive learning rate. Describe adaptive learning methods. So here we need to talk both about the concept of adaptive learning rate, and we also need to give you examples of optimization algorithms that are known to be of adaptive nature. So when it comes to the traditional GD, HGD, or HGD with momentum, so all the optimization algorithms that we spoke about before, all these algorithms have single quality in common, that they are using exactly the same learning rate when updating all model parameters, independent whether those are weight parameters, whether those are bias factors, or whether they are different weight factors, so weight parameters for different hidden layers. Now, the adaptive learning process and adaptive learning rate in a neural network is quite different from this constant learning rate. So this learning rate, which we saw before, defined by eta, in deep learning can play a crucial role when it comes to defining the step size. So how much we need to update the weight parameters, how much we need to update the bias factors, and it basically defines the amount of update we need to make. So what the adaptive learning process does is that it says we should not use exactly the same learning rate across all these parameters. Instead, we need to look at the training data and we need to look at the feature, and based on that, understand and adopt the learning rate, so the step size that we need to use when updating the model parameters. Because it can be that we have these different features and one feature can require a different amount of updates, so this learning rate, the step size, versus the other features that will require different sorts of updates. And that's exactly what this adaptive learning optimization process does. So it handles diverse data It's able to look into these complex data sets and look into these features. And it then tries to update the different model parameters based on the corresponding information that it's getting. So from the learning process, from computing the gradients, and then from these patterns in the different features. So in this way, we are adapting the learning rate accordingly. And each model parameter will have its own learning rate. So this will then avoid having a stagnation and will definitely reduce the oscillations, because it helps you prevent getting stuck in a local minimum and not being able to discover the global optimum, which is a common issue when we have a fixed learning rate. Now, when it comes to different examples of adaptive learning rate, when we have different learning rate and the learning rate is being adapted based on the information that it's getting from the algorithm and training data, there are a few that you can mention. And one of the most popular optimization algorithms that is also of adaptive nature is the AdamW optimization algorithm. So AdamW, that specifically stands for Adaptive Moment Estimation, which is then the algorithm that adapts the learning rate accordingly and therefore is also known to have much better performance when it comes to optimization. So another example is the RMSProp. RMSProp stands for the root mean squared propagation. And this algorithm has been introduced as one of the Coursera courses about deep learning. And from then on, many people have been using it and experimenting with it. Another adaptive optimization algorithm is the adaptive gradient algorithm, which is the AdamW. So this also adjusts the learning rate based on what we're calling cumulative squared gradients. And it's particularly useful when you are dealing with sparse data. So this is basically at high level the summary of the adaptive optimization process, what it means to adapt the learning rate, the impact of it on the deep learning model performance, as well as the examples of few adaptive optimization algorithms largely used across the industry. The next question is, what is RMSProp and how does it work? So we just saw that RMSProp is one of the examples that can be defined as an adaptive optimization process. And RMSProp stands for the root mean squared propagation. And it is like GD, SGD, and SGD with momentum, an optimization algorithm that tries to minimize the loss function of your deep learning model to find the set of model parameters that will minimize the loss function. So what RMSProp does is that it tries to address some of the shortcomings of the traditional gradient descent algorithm. And it is especially useful when we are dealing with vanishing gradient problem or exploring gradient problem. So we saw before that a very big problem during the training of deep neural network is this concept of vanishing gradient or exploring gradient. So when the gradients start to converge towards zero, so they become very small, they almost vanish, or when the gradients are so big that they are exploding. So they are becoming very large and they result in a large amount of oscillations. Now, to avoid this, what RMSProp is doing is that it is using an adaptive learning rate. It's adjusting the learning rate, and it is using for this process this idea of running average of the second order gradients. So this is related to this concept of Hessian. And it is also using this decay parameter, which takes into account and regulates what is the magnitude, the average of the magnitudes of the recent gradients that we need to use when we are updating the model parameters. So basically, what is the amount of information that we need to take into account from the recent adjustments? So in this case, this means that parameters with large gradients will have their effective learning rate to be reduced. So whenever we have large gradients for a parameter, we will be then reducing the gradients. This means that we will then control the exploding gradient effect. And of course, the other way around holds true. In case of RMSProp, for the parameters that will have a small gradients, we will be then controlling this and we will be increasing their learning rate to ensure that the gradient will not vanish. And in this way, we will be then controlling and smoothing the process. So the RMSProp uses this decay rate, which you can see here too, this beta, which is then a number usually around 0.9, and it controls how quickly this running average forgets the oldest gradients. So as you can see here, we have this running average Vt, which is equal to beta times Vt minus 1 plus 1 minus beta times Gt squared. So this is basically our second order gradient. So then what we are doing is that we are taking this running average and then we are using this to adapt and to adjust our learning rate. So you can see here in our second expression, the theta t plus 1, so the updated version of the parameter is equal to the theta t, so the current parameter, minus, so we are subtracting, the learning rate divided to square root of this Vt, square root of this running average, and we are adding some epsilon, which is usually a small number, just to ensure that we are not dividing this eta to 0 in case our running average is equal to 0. So we are ensuring that this number still exists and we do not divide the number to 0. And then we are simply multiplying this to our gradient. So as you can see, depending on our parameter, we will then have a different learning rate and we will then be updating this learning. So by adapting this learning rate in case of RMSProp, we are then stabilizing this optimization process. We are then preventing all these random movements, these oscillations, and at the same time, we are ensuring smoother convergence. We are also ensuring that our network, especially for deep neural networks, it doesn't suffer from this vanishing gradient problem and from the exploding gradient problem, which can be a serious problem when we are trying to optimize our deep neural network. The next question is, what is AdamW and why is it used most of the time in neural networks? So AdamW is an adaptive optimization algorithm that is known for its dynamic learning adjustments based on the first and the second moments of the gradients. So AdamW, like RMSProp, is another adaptive optimization algorithm which adapts the learning rate accordingly in order to reduce the amount of oscillations and to improve the optimization algorithm's quality. What AdamW tries to do is that it tries to bring these benefits of two different algorithms together. It tries to combine the idea of momentum from SGD with momentum with the idea of the RMSProp by using the running average of the second order derivative, so the second moment. And by combining the two, it tries then to take the benefits of these two worlds. So when it comes to the AdamW, it can be represented by this mathematical representation. You don't need to know it, but I always think it helps to bring perspective to how it combines the two worlds, the RMSProp and SGD with momentum, and why it is actually so useful. So when we look in here, we can see that the first one is the momentum term. So the mt is equal to beta 1 times mt minus 1 plus 1 minus beta 1 times gt, where the beta 1 is the first parameter, which is simply a constant, and the beta 2 is also a constant, a hyperparameter, both of which we can actually tune. So in here, you can see gt and gt squared, which are simply the first moment and the second moment of our gradients, where second moment is known to be better estimate, less noisy compared to the first moment. So what we are trying to do is that we are on one hand using this idea of momentum in order to reduce the amount of oscillations that the optimization algorithm is making. And in this way, we are improving the optimization process and getting a better quality. And on the other hand, we are also introducing this idea of velocity, which comes from the RMSProp, which then will result in better, less noisy estimate of the gradients. So by doing this, what we are trying to do is that we are adjusting the learning rate throughout the training process, and we are making it more effective across different scenarios. So for scenarios where HGD with momentum would have been better, Adam will incorporate this. And where it would be beneficial to use RMSProp, then Adam would again add the other optimization algorithms. And that's why Adam has been proven across the entire industry to be very effective, and people are using it across the industry for a wide range of problems and applications. So as you can see, once we have our running average for the first order derivative and the running average for our second moment gradient, then we are also adjusting, so we are correcting this momentum and the velocity by dividing this mt. So we are taking the mt and we are dividing it to 1 minus beta 1t, because we want to adjust for the bias when it comes to this momentum. And then we are also adjusting the velocity. So Vt hat is then the adjusted version of the Vt, because we take the Vt and we divide it to 1 minus beta 2 to the power t by using the beta 2 as our hyperparameter, as our second bias vector. And then we are using this adjusted running average for the first moment and the adjusted version of the running average of our second order gradient in order to update and adapt our learning rate. And as you can see here, what we are doing, we are taking the learning rate alpha, we are multiplying it by the adapted and adjusted momentum term, and then we are dividing it to the square root of this velocity term, or Vt hat, plus some epsilon, which is usually a small number, just to ensure that we are not dividing this number to 0. And we are using this to subtract from the theta t, so the current parameter, to get our new updated parameter theta t plus 1. So when it comes to the benefits of using the Adam, first of all, Adam incorporates these benefits from multiple optimization algorithms to ensure that the quality is in place and the efficiency is in place, and the optimization algorithm is able to handle different scenarios. The efficiency with sparse gradients is another advantage of Adam Optimizer, because Adam is particularly efficient when dealing with this sparse gradient. And the other advantage of Adam is that it's able to balance the speed and the stability. So Adam generally converges much faster when it comes to the converging to the global optimum compared to algorithms such as HGD. And at the same time, it also tends to be more stable because it's able to control the learning process compared to the algorithms that only use the first moment. Whereas the Adam is also using the second order gradients. So the second moment. And the final advantage of Adam is that it is robust. So it's known for its robustness in various conditions and various scenarios, which also means that it is less sensitive to hyperparameter choices. And this is especially important when it comes to the initial learning rate. And this makes it much more easy and user-friendly for a large range of applications, especially when you are someone who is just learning deep learning. Then it can be a bit difficult to tune your hyperparameters. It can be difficult to identify these initial values that you need to use for your algorithm. And Adam is then less sensitive to this choice of learning rate, which can be really important. What is AdamW and why it is preferred over Adam? So here we are, of course, referring to the Adam optimization algorithm that we just discussed, and the AdamW is simply the adjusted version of the traditional Adam optimizer. So like Adam, AdamW is an adaptive optimization algorithm that is used to optimize the training of a neural network and to find the minimal point of the loss function by continuously adapting the learning rate and updating the model parameters. So the biggest difference in AdamW and Adam is the way they perform this regularization. So the traditional Adam has one specific disadvantage, which usually comes when dealing with deep neural networks. So unlike the traditional HGD with momentum, Adam is unable to properly generalize the model. And most of the time, when we are performing regularization with Adam, so let's say we are using L2 Regularization with Adam in order to penalize large weights and in order to address the overfitting problem of the algorithm, then Adam has shown in the industry when training different deep neural network to not generalize very well and to solve this problem of overfitting. So that's exactly what AdamW tries to do. It tries to address the specific problem of Adam such that we can have improved generalization and it can address the shortcomings of the traditional Adam, making it one of the best algorithms out there, and it's being used more and more across various applications. And this is especially true when it comes to fine-tuning already pre-trained model, because those type of models are known to have this problem of overfitting, and we need to have general model when the problem of overfitting will not be so present, and we will be able to pre-train the model, fine-tune the model based on this pre-trained model, and then use this on an unseen data, and the model will still perform well. So this basically solving the problem of overfitting and ensuring that we have improved generalization. That's what AdamW does. And the way it does that is that, like you can see here, unlike the traditional Adam with L2 regularization, for instance, what it does is that it adds this decay, so this penalization term, right in the update process when updating the model parameters. So the traditional Adam algorithm, when combined with L2 regularization, where Adam is the optimization algorithm and L2 is the regularization algorithm to solve the overfitting, what we do is that we add this lambda multiplied by theta t minus 1, where lambda is this penalization parameter we use to understand how much we need to penalize certain parameters. And this is to ensure that the model doesn't memorize the training data, and it ensures that the model is more generalizable. Now, when we do this, sometimes this doesn't help us that much to solve the overfitting problem. And the weight decay, so decoupling this weight decay from this gradient updates, and instead of using this as part of this gradient update, if we incorporate this directly as part of the model parameter updates, then it has proven to have much better impact in terms of generalization of the model. So when we add this regularization term, lambda multiplied by theta t minus 1, not to the gradient, but we add it directly when updating the model parameter as part of this entire expression, as you can see, multiplied with the learning rate, then this has shown to have much better impact in terms of solving the overfitting problem and making the entire trained model more generalizable, which will then ensure that we have better performance in specific scenarios, especially when we have deep neural networks or when we are fine-tuning pre-trained model. And this also means that the algorithm will perform equally well on an unseen data, unlike when we are using the traditional Adam, which in some scenarios doesn't perform generalization very well and it suffers from overfitting. The next question is, what is batch normalization and why it is used in neural networks? So batch normalization, to understand this concept, you need to know what is a normal distribution. So the standard normal distribution is a probability distribution function that has a mean equal to 0 and a variance equal to 1. And what batch normalization does is that it normalizes the activations per batch. Hence the name batch normalization. So batch normalization is this technique that is introduced to address the issue of this internal covariate shift in the neural networks. And what this refers is that there will be a change in the distribution of the network activations due to the changes in the parameters of a neural network. So every time when we are using the backprop, we are computing the gradients, then we are using the optimization algorithm to update those model parameters. This then will introduce this change in the distribution of activations, which can then destabilize our neural network. And it's something that we don't want to have. For better performance of our algorithm and our neural network, we want our batches to have certain preferred distributional properties. So we want it to be, for instance, normally distributed, which is known to be one of the most go-to distribution functions in statistics, in machine learning. And by normalizing the activation, so once we compute our z-scores, we apply our activation function and we get our activations, then we can normalize these activations by computing the mean and by computing the variance of these activations across the batch, so for all the observations per batch, and then we can use this in order to normalize the activations. Now, you will most likely be familiar with this concept of normalization if you have used traditional machine learning models. But let's quickly look into the mathematical definitions, just in case you also need to provide this as part of your answer. So when we look in here, you can see that we are computing the mean of all the activations, where xi defines the activations and m is the number of observations per batch. We are taking the sum of all these activations and we are dividing it to the number of observations per batch. This then gives us our batch mean, so mu batch. And then we can also compute the corresponding variance of the batch by taking this activations xi and subtracting from this the mean of the batch and taking the square of this, so the square difference of the activations and the mean of the batch, and we are taking the sum of them for all the batch observations, so m elements, and dividing it to the number of all observations per batch. In this way, we can find an estimate of variance of this batch, and we can then use this to normalize the activations of this batch. So as you can see here, we are taking the xi, so activations, we are subtracting the mu b, the mean of the batch, and dividing it to the square root of the sigma b squared, so the variance of the batch, and we are adding some noise, so the epsilon, to ensure that we do not divide this number to 0. And then once we have these activations, we can then use this normalized activations to obtain our predictions. So this picture is a common picture that is used to visualize this idea of batch normalization, because here we have all the observations of the batch. So we have n different observations according to this picture. And then we need to normalize this per feature. So you can see that we are normalizing per feature all the observations per batch. So we are using all the observations per batch to find the mean for that feature and to find the variance of that feature. And then we are computing the normalized activations. Now you might be thinking, but why do we even normalize it beside of stabilizing the neural network? And how does that even affect the stability of the neural network? So when we perform normalization using this batch norm introduces this 2 trainable parameters per activation. So one for the scale and one for the shift. So the scale is then this mu, and then the shift is then the variance. So once we have this step ensures that the normalization process doesn't diminish the representational capacity of the network. So in this way, what we are doing is that we are stabilizing the distribution of the activations across different layers. So in each layer, we don't have entirely different distribution for activations. And when we have similar distributions, and this is just normal, then we will have more stable learning process. And this will then allow for higher learning rates, which will then accelerate the training process of a neural network. And when we are accelerating the training process, we are making a lesser amount of these oscillations, which we saw was a big problem as part of the traditional HGDs. And the lesser we are making oscillations, the higher is the chance that we will quickly and smoothly go towards the global optimum, and we will find the global optimum of our loss function. The next benefit of using batch normalization is that it reduces the sensitivity of the algorithm to the initialization. So when we are training our neural network, we need to have initialization for our weights and for our bias vectors. And this weight initialization can influence significantly the final outcome of the neural network, and it might even entirely change and put the algorithm towards wrong direction, so towards local minimum, when we are trying to optimize the algorithm. And when we perform batch normalization, then the algorithm will be less sensitive to these initial values of the weights, which means also that we will have higher chance to find a global optimum instead of the local optimum. Then the final indirect impact of this batch normalization is the regularization impact. So batch normalization is usually done for stabilizing the neural network. But the indirect impact of this regularization, the indirect impact of this normalization is that it has a regularization impact. So what then this algorithm does is that it slightly regularizes the neural network, and it reduces the need for using other regularization algorithms that would try to solve the overfitting problem. And the way model does this is that by normalizing the activations, it ensures that some of the neurons doesn't get too high activations, and this will then be some noise points, which will end up impacting the outcome of the entire neural network. Because if the training happens on some noise data points as part of a training data, and the model focuses on these noise points and learns this, memorizes these data points, which are not supposed to be memorized, then the updates that the model will make will be based on these too high but noisy points. When we are performing normalization and we are reducing the impact of these noise points, it means also that we are also reducing the risk of the model following this noise too heavily and impacting the entire model update, which then on its turn reduces the risk of overfitting. So it has a regularization impact for neural network. The next question is, what is layer normalization and why it is used in neural networks? So layer normalization, like batch normalization, tries to stabilize a network and reduce the internal covariate shift of the activations to ensure that the neural network is able to properly learn in a stable way dependencies in the data. So we just saw that batch normalization uses the entire training data of one batch when computing the mean and the variance and performing normalization per feature. Now, unlike the batch normalization, the way layer normalization does this normalization process is that it computes the mean across all features, not one, but all features for a single training observation, and does it the same for the variance. So it computes the variance across all features but for a single training observation, and then uses this to normalize these activations. So the reason for this change is that in some cases, in certain neural network architectures, the feasibility is not there. So we cannot even calculate. It just doesn't make sense to perform normalization across all training observations because of the structure of our architecture and also the input data nature. For instance, when we have CNNs, based on this architecture, we can then use the batch normalization easily. But when we have this architecture such as RNNs or LSTMs or GRUs, then using batch normalization is not effective, and layer normalization has proven to be much more effective in those cases. So therefore, for this different sorts of architectures, we can then use layer normalization whenever it is not possible to use batch normalization. Layer normalization is largely used also in the state-of-the-art transformers, which are a part of the trendy large language models such as GPTs, which are encoder only, but also the decoder only architectures such as BERT. And if you're wondering why layer norm is particularly used in architectures like RNNs or LSTMs or GRUs or transformers, it is because in those kind of architectures, the batch size is either small or it can vary. And whenever we have this varying or small batch sizes, then batch norm usually is not effective. And unlike batch norm, layer norm in those cases is particularly effective. So like in RNNs or in GRUs or LSTMs, where regarding of the batch size, which can be different, the layer norm will still perform effectively when it comes to stabilizing the network. The next question is, what are residual connections and their function in neural networks? So, residual connections have a very important function in neural networks, and specifically, they try to optimize the performance of neural networks by combating the infamous vanishing gradient problem. The residual connections, they play a key role in deep learning architectures like ResNet, transformers, the GPT series large language models, as BERT model. So if you look at the paper called Attention is All You Need, then you will most likely see as part of the architecture in each of these layers, beside of having the actual layer, you will also see this additional layer which says add and then norm. So this is exactly where the layer normalization comes and the residual connections are added. So what the residual connection does is that in this, unlike the typical neural network, where the input is simply transformed through the weights and the bias vectors into the corresponding activations to produce the output, in case of residual connections, we are adding the original input directly on the output of this layer. And this is often referred to as a shortcut or a skip connection. And the reason why it is called a shortcut or a skip connection is because the gradients are simply skipping through this transformation of this computational graph of being transformed towards the multiplication with the weights, adding bias factors, and then using the activation function as transformation. And instead of that, it has also a direct shortcut towards contributing to the final outcome. So as you can see here, with residual connections, we have the output equal to the fx, which is the transformation, so it's the output of that layer, plus the actual x, which is the input. So going back to this example of the transformer model in the original paper, Attention is All You Need, you might recall from the transformer architecture this part, which is the left part, so the encoder part of the transformer model. It's also used as part of the GPT series, so the general pre-trained model, where we are, so the transformer model, where we are using the input, so the input embeddings on the top of that positional encodings based on the sinusoids and cosinusoids. And then on that, after that, we are transforming this into queries, keys, and values, if you're familiar with the transformer model. And then this goes as an input to the multi-head attention layer. So if you're not familiar with this architecture of transformers, just forget about that. Don't mind the details. Just think of like this multi-head attention layer as a layer in your neural network that tries to learn the interdependencies between elements of your sequence. So what we are doing here is that beside of providing this input, those positional encodings added on the top of the input encodings, beside of giving that as an input to the multi-head attention layer, which then gives us an output, the transformed version, we are also giving this value, this input, you can see with this arrow, going to the on the top of that output. So we are getting the output from the multi-head attention layer, and on the top of that, we are performing layer normalization, and we are adding the input on this output. And this is exactly what we are doing as part of residual connections. We are adding the input on the top of that output. Now, the reason why it is called shortcut, it is because when computing the gradients, the gradient will then go through these transformations. We need to compute the partial derivative of the loss function with respect to the weights, and for that we first need to calculate the partial derivative of the loss function with respect to the z-scores, and then we need to compute the partial derivative of the z-scores with respect to the weights, and then use the two and use the chain rule to compute the partial derivative of the loss function with respect to the weights. Now, this entire transformation of these gradients will result in many cases the gradient coming very close to zero and vanishing. So this is the infamous vanishing gradient problem. And to avoid this, what we are doing with residual connections is that we have also this shortcut. So you can see that we are not only performing this different transformation. So we have X, then we have the weight layer, then we have the rectifier linear unit activation, then we have weight layer, and then we are getting the output, which is the Fx. And on the top of that, we are also adding this X, so the initial input on the top of this output. This is what we are calling residual connections. And the reason why you can see that we have this idea of shortcut, so the gradient is able to flow into the network not only through these transformations, but also directly towards the gradient, is because of this mathematical derivation here. So if we look at the output, y is equal to x plus fx, where x is the input that we are adding on the top of the output fx, you can see that if we take the partial derivative of this function, x plus fx, with respect to the x, then what we need to do is we need to apply the chain. So we need to take the partial derivative of the e with respect to the y, then multiply it with the partial derivative of y with respect to the x, which is equal to the partial derivative of e with respect to y, so exactly the same as we have here, but then multiplied with 1 plus fx, or first order derivative x, I have to say. And the reason why it is this value, because as you can see here, we need to take the partial derivative of y with respect to x, and as y is equal to x plus fx, when we take the partial derivative of x plus fx with respect to x, using the rule for summation, the differentiation of sums, then this is simply equal to the derivative of the x with respect to x, which is 1, plus the derivative of fx with respect to x, which is f, and then this not x, which basically is the first order derivative of fx with respect to x. So as you can see here, when we open this parenthesis, this is the same as taking the partial derivative of e with respect to y, and then adding to this the partial derivative of e with respect to y times f naught x. And this is simply opening parentheses, so 1 multiplied with this value, which gives us the first order derivative of e with respect to y, plus, and then we have this second part of the within the parentheses, which is the f naught x, multiplied with the partial derivative of e with respect to y, which is simply the partial derivative of e with respect to y multiplied by f naught x. So what we can see here, and the reason why I am explaining this mathematical derivation, is that you can see for yourself that the gradient in this case, with respect to x, will be able to not only flow through this part, which is the multiplied by f naught x, which has gone through all these transformations of the weight and an activation function, but also directly, because we have here this term, partial derivative of e with respect to y. And why this is helpful and how this is reducing the vanishing gradient problem is because when we have these multiple layers, by the time we come from this very deep layers to the very earlier layers, our gradient goes through all these transformations of the weights, activation functions, and then it ends up becoming very close to zero. So it's vanishing. And if we have this opportunity for the gradient to go through the shortcut and flip through and skip some of the layers, we will have a higher chance of this gradient to not vanish and to actually reach from deeper layers to the initial layers. And that's exactly what we want to do, and this solves the problem of vanishing gradient. What is gradient clipping and their impact on neural network? So we just saw the residual connections, and we saw that residual connections, especially for deep neural network and specifically for the cases like RNNs, LSTMs, when we have the sequential nature with too many layers, we can have this vanishing gradient problem, and residual connections can help you solve this problem. Now, gradient clipping is solving the opposite problem. So it's solving the exploding gradient problem. Whenever we have certain deep neural networks like RNNs, LSTMs, because we are each time using these transformations and we are using a cumulative nature and multiplying all these weights towards each other through this process, and we are using the previous hidden state to update the new hidden state, so the next hidden state and the next one, it also means that when we are going through these layers, during the optimization process, after backprop is done, we need to perform all these transformations. And by the time we come through the earlier layers, it can be that we have exploding gradients. So the gradients become so large that it starts to impact the entire performance of the model. We are starting to make too big over jumps, and the updates that we are starting to get and optimization process is starting to make too much of these oscillations towards different directions. So we are seeing this erratic behavior as part of our optimization process. And that's definitely not something that we want to have, because exploding gradients means that we have unstable neural network, and this also means that the update of the weights will be too large, and this will then result in not well performing and not properly trained neural network. Now, to avoid all these problems, the way we can solve this exploding gradient problem is by using the gradient clipping. What gradient clipping does is that it basically clips the gradients at a certain level. So there is a threshold, which is the parameter that we are using for gradient clipping. And whenever the gradient becomes too large, so higher than the threshold, then we will be clipping that gradient to ensure that this gradient is not too large and we are not updating our weight parameters or bias factors too much. So in this way, what we are doing is that we are kind of stabilizing our neural network, which is especially important for architectures like LSTMs, RNNs, GRUs, which have this sequential nature of the data with too many layers. And in this way, we will ensure that we do not have these erratic jumps in our neural network optimization process, and we will end up with a stable network that is able to properly learn the interdependencies. So the key idea behind Xavier Initialization is to keep the variance of the activations and the gradients consistent across layers. The way it is done, it is by setting the initial weights based on the number of input and the output neurons in a neural network. So the way it works is that it looks into the n in, which is simply the number of neurons as the inputs that go into that layer, and the n output, which is the number of neurons or the output as part of that layer, because in each layer we have neurons that comes in and the neurons that come out. And this n in that comes in and n out that describes the number of neurons that go out is being used in order to define the distribution of these weights. So one way that the Xavier Initialization tries to stabilize the network and keep the gradients as well as the activations consistent and stable is by using certain statistical distributions with certain qualities that will ensure that the variance of the weights is constant. So we want to come up with a distribution from which we will sample our initial weights using the n in, which is the number of neurons that go into that layer, and n out, which is the number of neurons that go out of that layer, using that combined with the statistical distribution. So one way of doing that is by using the uniform distribution. If you are familiar with the statistical distribution function, the way uniform distribution works is that it always has these two parameters. It has a lower bound A and the upper bound B, and the distribution always lies within this specific area. It's like a rectangular area And the corresponding values, so the upper bound is the probability is 1 divided b minus a. So the probability for all the values that lie within that range is constant. It's equal to 1 divided b minus a. Now, why this is important in our case, it is because if we use certain a and b, in this case you can see when using square root of 6 divided to square root of n in plus n out as a lower bound, and its positive version, so square root of 6 divided to a square root of n in plus n out, then the variance corresponding to this random variable that follows uniform distribution with this lower bound a and lower bound the upper bound b will be then equal to 2 divided to square root of n in plus n out. So the variance of this random distribution will be this amount. And this means that every time we have this weight will then be constant. So the variation of it will be constant. And what does it mean if the weight has a constant variance? It means that it will always change in a similar amount. So it will not change too much with too high gradients, so exploding gradients. It will also not change too low. So the gradients will not be too small. So we will also combat the vanishing gradient problem. And that's why Xavier initialization can be so important and so significant, because it can help to stabilize the entire network. It can bring consistency into the variance of these activations and the gradients across different layers. And it will also reduce this risk of vanishing and exploding gradients, which will promote stability, and it will also improve the efficiency of your training process. And this process is particularly relevant for the sigmoid activation function and the tang activation function. Let's now look into the next question. So what are the different ways to solve vanishing gradient problem? So by now we have discussed many topics and many approaches where I have briefly mentioned that this helps to solve the vanishing gradient problem, for example. So here I will just summarize at high level very quickly what are the approaches that you can mention that solve the vanishing gradient problem. So the vanishing gradient problem firstly can be solved by using appropriate activation functions. So by using activation functions such as rectifier linear unit function or leaky rectifier linear unit function that do not suffer from saturation, these activation functions can help to solve the vanishing gradient problem and ensure that your gradients will not vanish in those deep networks by the time you come from these very deep layers to the early layers. If you use so don't use the sigmoid, don't use the tang, but use the leaky ReLU or ReLU in order to combat the vanishing gradient problem. Another way that you can solve this problem is what we just discussed in the previous question, which is the Xavier initialization. So choosing an appropriate weight initialization technique can help you to combat the vanishing gradient problem. Another way to solve this problem is by performing batch normalization. So batch normalization indirectly will introduce stability into the network. And by normalizing the activations, it will also result in your gradients, which will be more consistent. And if your gradients are more consistent, it also means that you have lesser chance of having a problem of vanishing gradients. Then another way that you can solve the vanishing gradient problem, especially when it comes to sequence-based architectures like RNNs, LSTMs, GRUs, in all those cases, you can use residual connections. So residual connections will help you to open the door for the shortcut for your gradients to flip through your network without going through all these transformations. And this will then, on its turn, help you reduce the risk of vanishing gradients. Then the final way of combating the vanishing gradient problem is by using an appropriate architecture. So whenever you have a choice of choosing certain architectures, then try to make use of the ones that are more appropriate for your data, more appropriate for your problem, and this will avoid, at least at some extent, the chance of having vanishing gradient problem. If you are, for instance, making use of the transformer architecture, then in here we are automatically also adding this residual connections and layer normalizations after each layer, and this helps you combat the vanishing gradient problem at some extent. And if we are, for instance, using the AdamW, this also helps you regularize the network and in some way also solve this problem. The next question is, what are the ways to solve exploding gradients? So one way of solving exploding gradients, like we just spoke about, is the gradient clipping. So gradient clipping can help to keep this threshold and ensure that every time the gradients are checked with respect to this threshold. And every time when we have gradients that are about to explode, so they go beyond the threshold, it will then clip the gradients and it will ensure that these gradients will not go over this level. And this will then solve the problem of exploding gradients. Another way you can solve this problem is by using the weight initialization in a proper way. So as we saw before, Xavier Initialization will help us to not only solve the problem of vanishing gradients, but also the problem of exploding gradients. Because by keeping the variance of the weights constant, we ensure that the gradients will not explode, so not grow too much, also not grow too little, so to vanish. So in this way, weight regularization and weight initialization will also help to combat the exploding gradient problem. The next question is, what happens if the neural network is suffering from overfitting related to weights in neural network? So there are two portions of this in this question. And the first part refers to the overfitting problem. So you need to show that you understand how overfitting relates to neural network. Usually this is similar to the overfitting of machine learning models. And the second part is to relate the overfitting to the weights in neural network. So let's start with the first part. So what is overfitting? Overfitting happens when the model that we are using, in this case a deep learning model, it starts to memorize the training data. And when training the model, it tries to ensure that the model performs well specifically on the training data. Even though training data might contain some noise points, not general points, some outliers. And when we train our model on this type of data, and the model starts to memorize this, and we use this fitted model to train on an unseen data, then what we will see is that this overfitting model is not performing well on an unseen data. Whereas our entire goal is to train the model on a training data in such a way that this final version, the fitted version of the model, will properly perform on an unseen data. That's our entire goal. Otherwise, we would not be using predictions in the first place. We want to have a proper prediction with high accuracy for a future data or unseen new data. And that's something that overfitting causes a problem with, because it makes the model less generalizable. It will not generalize well on unseen data. Now, how it is related to the weights of the model. So large weights in a neural network will make the model very sensitive to its input data, which might also include outliers or noise data. And when the model follows training data too closely, which also includes these unusual points, then this model will not generalize well to the new data. And therefore, that's something that we don't want to have. We want to solve the problem of overfitting to ensure that our model is generalizable and will also perform equally well, or at least at some extent very similar to the performance of the training data when we introduce the model to the new data. The next question is, what is dropout and how does it work? So dropout is a regularization technique commonly used in deep learning specifically in order to solve the problem of overfitting. So we just saw in the previous interview question that overfitting can cause a lot of problems when training neural networks. And we want to have ideally a model that generalizes well on an unseen data. And one way to make our model more generalizable and improve the performance of our model is by using a regularization technique. And one very popular regularization technique in neural networks is dropout. So what dropout regularization does is that it randomly drops out or deactivates a subset of neurons in your neural network during each training iteration. And the way it does is that it takes this probability, or you can also say proportion, and this p is simply a value between 0 and 1. And this refers to the amount of or proportions of neurons that needs to be randomly deactivated. So P is the dropout rate. And we are saying that the RGL, which is simply the activations in the layer L, that this random variable follows Bernoulli distribution with 1 minus P probability, where 1 minus P is simply equal to the amount of neurons that should not be deactivated, so amount of errors that should be activated. And if you have P as the deactivation rate, then 1 minus P will be the activation rate. And why Bernoulli? Because if you are familiar with some very popular statistical probability distributions, you will know that Bernoulli distribution helps us to express and define random variables that have two possible outcomes. There can be either success or failure. So there can be either dropping out or not dropping out. We can either activate or not activate, so deactivate neurons. And that's why we are saying that our activations in that specific layer, let's say layer L, can be described by a random variable that follows Bernoulli distribution with activation rate of 1 minus P, where P is the dropout rate. So think of it like if we want to randomly deactivate or drop during the training iteration 20% of our activations of our neurons, then this P will be equal to 0.2, which means that our activation rate will be equal to 0.8. So our layer will follow a Bernoulli distribution with 0.8, as 0.8 being equal to the success probability. So then what we will doing is that during only the training process, in each iteration, we will randomly deactivate and drop out some of the neurons. And in this way, we will ensure that every time our model sees only 80% of the activations. And how does this help to solve the overfitting? Is because we reduce the chance of our model seeing the noise points and memorizing the training data. Because if our model sees every time 80% of the neurons, and every time it's changing from iteration to iteration, this 80%, because the process is random, then we have smaller chance for our network to every time see the same noise and to memorize the training data, because we are kind of decorrelating the training process. And what this then will help to do is that it will make our neural network more stable and less dependent on certain neurons. And it also means that it will generalize better. It will reduce the chance of overfitting. There is, however, a catch, which comes that we are performing the dropout only at the training data. And later on in the upcoming questions, we will see how we can answer those type of questions. What exactly we need to do given that we are performing dropout only on the training data. The next question is, how does dropout prevent overfitting in neural networks? So we already answered majority of this question, so I will just at high level summarize what I just said as part of the question 41. So the way dropout prevents the overfitting in the network is that it randomly deactivates P% of the neurons during the training process, which then reduces the dependency of the neural network on certain data points and reduces the chance of the network to memorize the training data. In this way, the network encourages the feature redundancy and also helps to generalize the model better. The next question is Dropout like random forest? So in this question, your interviewer wants you to test through a very tricky way whether you understand the differences between Dropout and random forest as well as their similarities. Now, let's first start with the common goal that the two algorithms have. So both Dropout and the random forest, they aim to improve the robustness of your model, and they reduce the chance and the risk of overfitting by introducing randomness and diversity in the training process. You might recall the random forest algorithm, which is an ensemble machine learning algorithm, can be used for both classification and for regression. And the way algorithm works is that it tries to use the different bootstrap samples, which are copies of the original training data only with replacement, and uses this different training copies in order to build different trees. But it does this by decorrelating the trees, so making them uncorrelated, unlike the backing, by using randomly selected M features when performing the splitting of the trees. So when the trees in random forest are built, because in this recursive building process, in each step, the algorithm randomly selects M out of all P features when splitting the tree. So when making this decision of where we need to split the tree and to what region the observation needs to be assigned, this introduces randomness to the algorithm. And this randomness helps to decorrelate the trees, and then the algorithm ends up having B uncorrelated different decision trees, and then it combines them all, therefore it's called also ensemble algorithm, and then takes the average across all these different B trees in order to get the final prediction. So in case of classification, that's the majority class. In case of regression, that's the average of all the outputs. Now, this helps the random forest to combat the overfitting, unlike the bagging. And as the average of uncorrelated variables has a lower variance than the average of correlated variables, in this way it helps to reduce the variance. And this then on its turn helps to reduce the risk of overfitting and makes the model more generalizable. So Dropout also tries to kind of decorrelate the process. Only the way it does it is by deactivating certain neurons, and in each iteration use a different portion of training data in order to train the model. And on its turn, this helps to avoid overfitting and avoid the network memorizing the training data. So in both ways and in both approaches, the models are introducing this random component Dropout by randomly dropping certain neurons, random forest by randomly selecting M different features when performing the recursive splits and building decision trees, in order to make the models more generalizable and reduce the risk of overfitting. Now the key differences. So how Dropout and random forest are different. Well, Dropout is a technique with a single model. We have just a single neural network. We are using exactly the same training data, and we are randomly dropping neurons in order to, in each iteration, have a different portion of training neurons in order to make the model more generalizable. Unlike the random forest, which is an ensemble technique. So it uses B different copies from the original data that samples it with replacement, and then uses this B different data sets in order to build B different trees, and then combine this B different models to create single model. So this means that the two algorithms work entirely different. Also, one is more a regularization technique. The other one is an actual algorithm that can be used on its own. The next question is, what is the impact of Dropout on the training versus testing? When we were discussing the Dropout, I briefly mentioned that Dropout is only applied on the training data, which means that we are only randomly deactivating the activations as part of our training process. But this also means that the neurons have smaller and specifically 1 minus p probability of being activated during the training process. So we are reducing the probability of a neuron to be selected for being activated. And this will then introduce inconsistency when it comes to the testing process, because we are applying the dropout only during the training. This also means that we need to address this reduce in the activation probability when we are performing the testing. So given that P% of the neurons during the training are dropped or deactivated, we need to compensate for this, and we need to ensure that we have consistency in the input size. And for that, what we need to do is that we need to scale the activations in the testing by 1 minus p. And in this way, we will then compensate for the small probability difference that we were making when we were dropping out certain activations. So just as an example, if the dropout rate is 20%, so 0.2, this means that during the training process, the neurons have 80% probability of being activated and 20% chance of not being activated. It means that during the testing, we need to scale the activations by using 0.8, so 1 minus p. The next question is, what are L2 or L1 regularizations and how do they prevent overfitting in neural network? So both L1 and L2 regularizations are shrinkage or regularization techniques that are used both in traditional machine learning and in deep learning in order to prevent the model overfitting. So trying to make the model more generalizable, like the dropout. So you might know from these traditional machine learning models what this L1 and L2 regularization do. L2 regularization is also referred as rich regression, and L1 regularization is also referred as lasso regression. So what L1 regularization does is that it adds as a normalization or as a regularization or as a penalization factor that is based on this penalization parameter lambda multiplied by this term, which is based on the absolute value of the weights. So this is different from the L2 regularization, which is the reach regularization. And this regularization adds to our loss function the regularization term, which is based on the lambda, so the penalization parameter, multiplied by the squared of the weights. So you can see how the two are different. One is based on what we are calling the L1 norm, and the other one is based on what we are calling L2 norm. Hence the names L1 and L2 regularization. So both of them are used with the same motivation to prevent overfitting. What L1 does different from L2 is that L1 can set the weight of certain neurons exactly equal to 0. So in some way also performing feature selection. Whereas L2 regularization, it shrinks the weights towards 0, but it never sets them exactly equal to 0. So in this aspect, L2 doesn't perform feature selection and it only performs regularization. Whereas L1 can be used not only for shrinking the weights and regularizing the network, but also for performing feature selection when you have too many features. So you might be wondering, but how does this help to prevent overfitting? Well, when you shrink the weights towards 0 and you are trying to regularize this small or large weights, then these methods, such as L1 or L2 regularization, they will ensure that the model doesn't overfit to the training data. So you will then regularize the weights, and this will then on its turn regularize the network, because the weights will define how much of this behavior, erratic behavior, will be prevented. If you have too large weights and you reduce them and you regularize them, it will ensure that you don't have exploding gradients. It will also ensure that the network doesn't heavily rely on certain neurons. And this will then ensure that your model is not overfitting and not memorizing training data, which might also include noise and outlier points. Now, what is the difference between L2 and L1 regularization approaches? So I did briefly mention the difference of the two. Now let's look into a more detailed version of it. So L2 regularization, also known as rich regularization, adds squared weight values to the loss function. So it's also called L2 norm. So as you can see, we are taking the weights Wi, we are squaring them, we are summing them up for that specific layer, and we're multiplying it by a regularization parameter, also referred as penalization parameter, lambda. Hence the name LL2, which basically means that this is the regularization term for the L2 regularization or the rich regularization. Now, when it comes to the impact of this L2 regularization is that it will shrink the weights towards zero. But it does this in a very proportional way. So it tries to make the weights more equal towards each other. So it will have a bigger impact on the large weights because it will try to make it equal to the smaller weights, but it will have lesser impact on the smaller weights. In this way, it will try to proportionally spread over the weights towards different neurons. And it will try to ensure that all these different neurons have kind of equal, proportionally equal impact on the training process. Whereas when it comes to L1 regularization, which is based on L1 norm, also referred as lasso regularization, it adds to the loss function the added, so the sum of the absolute value of the weights. So you can see here that it's equal to lambda multiplied by the sum of all the absolute values of Wi, the weights of our neural network. So the way L1 regularization works is that it adds these absolute values, which then shrinks the weights towards zero. And in some cases, it sets certain weights, and specifically those small weights, exactly equal to zero. So in this way, L1 regularization punishes these small weights, so it's heavily shrinking those weights and set them equal to exactly zero. And it has less of a punishment effect and is less harsh on these large weights. And in this way, it also performs feature selection because all the neurons, so the features that have a weight of zero, so they have their weight becomes zero, it means that they are no longer contributing to the network. So let's briefly look at the difference between the two in this table to clarify. So when it comes to the feature selection process, L1 performs feature selection, L2 doesn't because L1 sets certain weights exactly equal to zero. When it comes to the smoothing process, L1 it has a less smoothing effect because it's very harsh on the small weights. It sets them exactly equal to zero and less on the large weights. L2 is a bit different. It's less harsh of a method and it is more harsh on the large weights and much less on the small weights. It kind of proportionally spreads over the weights across all the neurons. It then ensures that the process is smoother. So then finally, the sparsity aspect. When it comes to L1, the sparsity is high because the model also performs feature selection. So it sets certain weights equal to zero, which means that it also automatically performs feature selection and it then reduces the dimension of the model and makes the network sparser. Whereas in case of L2 or rich regularization, the sparsity is low because the regularization process is not performing feature selection and it has no zero weights. The next question is, how do L1 and L2 regularization impact the weights in neural network when it comes to comparing the impact on large versus small weight penalizations? So in here, we can just summarize at high level, given that we went into detail of this as part of previous two questions, that L2 adds the square of the weights as a penalty. And as a result, the large weights are heavily punished, so they are reduced, versus the small weights, which are not so heavily and harshly reduced. This means that the L2 will distribute the error along and among all the weights, and this will lead to smaller but non-zero weights. And it will kind of proportionally spread over all the weights across the neurons. Now, when it comes to the L1 regularization, L1 significantly reduces the magnitude of the weights. So large versus small weights. The reduction of the weights when it comes to the large weights is much smaller. So the L1 regularization is less harsh on the large weights compared to the small weights. So given that we are using this absolute value of the weights, it means that the algorithm will be effectively remove the features from the model by setting certain weights exactly equal to 0. And those are usually the weights that have already been small. So it will penalize more harshly those small weights, and it will be very harsh on them, but not so much on the large weights. And in this way, we will end up removing those small weights by setting them equal to 0 and keeping only those large weights. The next question is, what is the curse of dimensionality in machine learning or in AI? So the curse of dimensionality is a known phenomena in machine learning, especially when we are dealing with these distance-based, neighborhood-based models like KNN or k-means, and we need to compute this distance using distance measures such as Euclidean distance, cosine distance, Manhattan distance. And whenever we have high dimensional data, so we have many features in our data, then the model starts to really suffer from the curse of dimensionality. So the complexity rises when the model needs to compute these distances between the set of pairs. But given that we have so many features, it becomes problematic and sometimes even infeasible to obtain those distances. And obtaining and calculating these distances in some cases doesn't even make sense, because they no longer reflect the actual pairwise relationship or the distance between those two pair of observations when we have so many features. And that's what we are calling the curse of dimensionality. So we have a curse on our ML or AI model when we have high dimension and when we want to compute this distance between pair of observations. And this can introduce data sparsity, this can introduce computational challenges, can introduce a risk of overfitting for our problem. The model becomes less generalizable. And it will also become a problem in terms of picking a distance measure that can handle this high dimension of our data. How deep learning models tackle the curse of dimensionality? So when it comes to the deep learning models, unlike the machine learning models, deep learning models do not suffer from this problem. So machine learning models, they need to, for them to work properly with high dimensional data, they need to perform feature selection. They sometimes recommend to use different sorts of feature selection techniques such as forward stepwise selection, backward stepwise selection, mixed selections, or other type of feature selection techniques or dimensionality reduction techniques such as PCA or factor analysis in order to reduce the dimension of our features before even providing them as an input to our machine learning model. This is not necessarily for our deep learning models, because deep learning models are able to counter this curse of dimensionality by learning these useful feature representations and reducing this data dimension that we have, applying regularization, and also using architecture specifically designed for high dimensional data. So basically, we don't need to perform feature selection when it comes to using this complex and high dimensional data in the deep learning, because deep learning models are specifically designed to be able to learn complex dependencies in the features, nonlinear patterns. So they do not need feature selection techniques to perform that for them. And instead, they just use techniques, regularization techniques such as L1 regularization, so lasso regularization, to not only perform regularization, but also to perform feature selection as part of the deep learning models itself. So, few ways that the deep learning models can prevent this curse of dimensionality, and the way that they do not suffer from this curse of dimensionality is by performing feature learning as part of the actual original deep learning process. So it also uses this dimensionality reduction techniques, for instance, uses autoencoders, variational autoencoders, to compress the input data and represent the input data with this compressed form, like the dimensionality reduction technique, but now as part of the actual architecture of deep learning model, and then learn the hidden factors from this already compressed data with lower dimension, and then reconstruct from this to get the final output. Now, another way that it does is by using regularization methods. And I briefly spoke about this just before by, for instance, using L1 regularization. Because L1 regularization reduces the sparsity and introduces sparsity by reducing the dimension of the features. By setting some of the weights equal to 0, it indirectly performs feature selection. And finally, if we use models such as CNNs and we use pooling layers, so pooling layers in convolutional neural networks, for instance, they automatically perform feature selection and they reduce the dimensionality of the problem. And in this way, they automatically combat the curse of dimensionality. The next question is, what are generative models? Give examples. So let's first start with the generative models. So generative models aim to model how data is generated. They want to learn the joint probability distribution, what we are often referring as P, X, and Y, which is the joint probability distribution of two random variables X and Y, where X represent the features of our data and Y represent the labels. So what generative models do is that they try to model the underlying data distribution. So they want to figure out how data was generated in the first place. And in this way, they can then generate new data instances. And they can also predict probabilities. And besides this, generative models are also great when it comes to unsupervised learning tasks. So from machine learning, you are most likely familiar with this idea of supervised versus unsupervised. When in case of supervised, we do have the labels, so the Y values. But in case of the unsupervised case, we don't have labels to supervise the learning process, which means that we need to perform the learning only using the features. Think about clustering, think about outlier detection or dimensionality reduction or some data generation. All these cases can be considered as unsupervised learning tasks, and generative models are great in doing so. Now, when it comes to the generative models, they are particularly useful in scenarios when we want to understand and we need to understand the underlying data distribution, or when we need to generate new data points. So let's say you want to generate synthetic data, or you have a lot of images and you want to generate new images that do make sense and they are similar to the input data, but they are new, they are novel, they are fresh. And this can be done by using generative models. And all the models that these days you hear about, for instance, the GPT series, the variational autoencoders, the GENS, so generative adversarial series, networks, all these models, they are generative models. And they are largely used for generating new images, generating synthetic data, for generating new speech. For instance, when there is a model that is trained on a large amount of the speech, you provide few examples of your speech, and then the model is able to generate new voice, so recording of based on the text, based on your own voice, but you haven't yet spoken that. That's generative model that is doing that.